ladies and gentlemen, thank you for coming to our 51st annual Geoscience Day. This year, I am 100% confident it is the 51st. Last year was our 50th, and there was some uncertainty as to whether it was the 49th or 50th. We checked afterwards. It is actually the 51st this year. If you don't know me, and I'm pretty sure just about everybody in this room at least does, I'm Dr. Nick Deardorff. I'm the chairperson of the Department of Anthropology, Geospatial, and Earth Sciences, and it is my honor and pleasure to welcome you to our annual Geoscience Day. This is a fun day in which we get to observe all of the hard work that our graduating seniors have done over the past year or more. There's a lot of effort that goes into the projects that you're about to hear about throughout the remainder of this Geoscience Day. It's not quite a full day of activities, but pretty darn close this year. We have quite a few presentations for you. Some of the hard work you're going to see for your very selves when the students come up here and present. But I want to highlight a couple of things. First, we need to thank Dr. Katie Farnsworth for helping to organize this and guide these projects this semester to completion. So would you guys join me and I also want to thank all of the geoscience faculty for helping as research advisors and helping along the way. So Dr. Warnock, Dr. Lewis, Dr. Farnsworth, I don't think I have a single student that's presenting this year, so we won't thank me at all. I did nothing, literally nothing to prepare this speech as we've discussed. So anyway, I think that's about all I had. Why? What's that?
We should thank IT, even though they're not
Oh,
anymore,
yes,
for attempting to help us and.
IT, thank you for trying to help us and then telling us to move to the next room over. Luckily, it was available and we're all good. But we do appreciate the prompt responses. Sometimes IT does not work. And thank you, Katie, for setting up the YouTube as well. So if we have any alumni join in, so that'd be great to be able to for them to be able to see it. So without further ado, it is exactly 8:35 now. We have our first presenter. Our first presenter, you can start coming up here to get yourself set up if you like, is Adriana Lastra Perez. She will be speaking on enhancing education through hydrology, assessing marsh run flood patterns, and innovative teaching strategies.
All right, good morning, everyone. I want to just first thank you all for coming to the Geoscience seminar. My research is going to be relating to hydrology, environmental education, and real-world applications, all centered around a small but significant waterway in Indiana Borough, Pennsylvania, known as Marsh Run. So urban environments that are prone to flooding are a pressing issue environmental-wise. So as you can see in this map, there is the highlighted orange region that is the Marsh Run region. It contains the small tributary streams of Marsh Run that start off outside of Chevy-Chase Heights, flows through Indiana, and then flows past IUP. So, like many urban streams, Marsh Run, like I said, is prone to flooding due to stormwater runoff, change in land use, and insufficient infrastructure. These two pictures are great examples of the impacts of urban flooding. On the right, I have I have the stream back erosion in Marsh Run. And on the left, I have the Marsh Run 2017 flooding events. This greatly impacts our local communities here and ecosystems. I took the initiative of going to part of the Marsh Run stream myself. I took 2 photos on March 7th of 2025. These photos were taken outside near the junior area high school that is located by North Avenue. This picture right here was actually taken behind a local dealership. And then the picture right here was taken behind the school garden in between the junior high and the senior high in Indiana. These pictures also illustrate that some of the pollutants and fallen trees that are contained within these streams. Like on this picture, you can kind of see there is a pizza box right here in the stream, and then there are some fallen trees that are feeding into the stream as well. So I'm actually a student teacher at the junior high, and it's located right where the start is near Vinegar Hill. So for my research, not only did I assess the hydrological patterns of Marsh Run, but I also created an educational curriculum that centers around the new environmental standards that are going to be implemented in the next school year. For this, I included a differentiated instruction lessons. So I created about 4 different instruction methods for 4 different classes for the earth and space science at the middle school. So like I said, I student teach for the 8th grade earth and space science classes. I have about 4 of them. So I use a different instruction method. So for period 3, I have about 22 students in total, and I did a technology-based lesson on Marsh Run. In period 5, I have about 16 students, and I did a self-guided reading lesson. In period 6, same as period 5, 16 students in total, and I did a hands-on fieldwork lesson. Lastly, with period 7, I have the same number of students as period 3, 22. And I did a direct instruction lesson. Throughout all my periods, I have many students with different academic accommodations, such as IUPs or individualized education programs. I also have students with reading support, students with ADHD, OCD, ESL, and autism. I also have a number of students here and there who are also in the gifted program. First, I did the technology-based lesson in period 3. This lesson started with me showing them a 7-second video of a truck plowing through an urban community in Marsh Run due to a flooding event. I had the students describe what was happening in the video and some objects and features they noticed as well. Next, I had them do a vocabulary exploration, where they explored 6 different vocabulary terms that are relating to streams, and they had to define these vocabulary terms in their own words. So they used that technology and internet to search up these vocabulary terms and then define them using their own words. Next, I introduced the sustainable solution of a rain garden, and they had to, again, write down rain garden definition using their own words and then find a picture online and cite that picture under this section. Lastly, I had them write 3 different ways for stormwater solutions to mitigate and help out the environments and the streams. In the extra time that we had in class, I had them do a quizzes activity, which is a technological online tool that helps them review certain concepts that they learned in class. In this case, we did Marsh Run, so we had everything that they learned within that lesson in the quizzes. Next, we have period 5. I did a self-guided reading comprehension lesson. I had made a small summary article, basically informing them on Marsh Run, so a little background, and then highlighted important vocabulary terms that they should know and later define using their own words. With reading this article, students also answered 10 self-guided reading questions. At the end of class, I had them do an exit ticket, which basically was they had to draw and label their own rain garden. Next, we have period 6. I implemented the hands-on lesson. So that means we actually took a mini field trip to Marsh Run, the street that was located outside of the school garden. So we walked there. I had them fill out a worksheet. It included them going to 4 different spots around the street, and they would describe the location. Then they would draw a diagram of the stream and label parts, and then answer 3 reflection questions surrounding the idea of the flow of the stream, some of the erosion that they can see along the stream, and lastly, identify any sources of pollutants in or outside of the stream, which we saw. Lastly, we have period 7, our direct instruction lesson. This lesson was, the majority of the lesson was me instructing them and informing them about Marsh Run using PowerPoint slides that I had previously made. In one of the activities, I had them do a notice and wonder chart. A notice and wonder chart is something that we do a lot in our classes, where we put up different pictures or videos, and they have to make observations about those pictures and videos. So for the notice part, they had to make observations of what they noticed in the pictures that I had put up, in this case, Marsh Run. So I put 4 different pictures, 2 from the 2017 flooding event and 2 others from current day Marsh Run. So they did at least three notices, and then 2 wonders. So what are some questions they have about the stream or the general concepts and area? Like period 5, I had them do an exit ticket too. So they did label and draw the rain gardens. And as you can see, I put some of their creations. So the day after I implemented the differentiated instruction lessons, we took a big field trip to 𝐚𝐴𝐤, where we are right now. They had this field trip centered around our past unit, the Earth in Space. And then one of the activities at this field trip, we ran the stream table with Dr. Farnsworth. And we basically had them observe different types of streams like the meandering channel and how they're impacted by water velocity. There was an aspect to this that was very fun. I had them do a hands-on portion of this where they could actually interact with the stream and alter it. So they would see how through time the flow of water would increase and then alter the stream. And then they also built blockages and like dams, and then they put different figurines and plastic houses around the stream to basically see throughout time how they would erode in the stream. So for my results, I had to measure knowledge retention using this these different types of lessons that I implemented. So overall, before I get started with results, I actually put a pre-test and a post-test for them to complete. So for the pre-test, I actually gave them the pre-test prior to the differentiated lesson, and then the post-test was given the day after the field trip. So when I was analyzing these results, the pre-test average score was about a 6.25 out of 10. Meanwhile, the post-test was increased to a 9.35 out of 10. So this all led to a 49.6% improvement in knowledge retention. I noticed that throughout all the classes, the scores increased, some more dramatically than others. I sectioned them off in this chart by period and their own lesson. So period 3 was in purple and they did technology. Period 5, they did self-guided in green. Period 6, blue, hands-on, and then the orange, period 7, direct instruction. And then the red shows us our post-test scores. Now, when I was analyzing further calculations, I noticed that period 5 and period 7 had the most increase in knowledge retention, about over a 90% improvement rate. So that means, for my conclusion, the self-guided reading lesson and the direct instruction lesson were the better instructional methods to use for this research. I just want to acknowledge real quick my mentor teacher, Mrs. Lisa Adams, for her guidance and support throughout my whole student teaching experience and for helping with my research as well.
Do you have any either measurements or just anecdotal feeling which of those instructional methods the students like the most? Because I learned before I even walked into a classroom as a teacher that direct instruction is deadly, or it was in the classroom. I thought it was not very dynamic. What did they respond to, in your opinion?
So with direct instruction, well, to start off, it's a middle school, so a lot of these kids are allergic to sitting in a chair and sitting. So I took a lot of breaks when I did this direct instruction. I forgot to mention, but during me, instructing them, I had breaks where I had them discuss in groups, and they actually kind of enjoyed it and were actually very engaged and intrigued in the Marsh Run stream because it's local. So they're like, oh, like I didn't know that this was here. But it seemed like they actually did enjoy it. At times I really did have to take breaks because it was getting a little bit, too much. But they did like it, although some of them did complain because they didn't get to do going outside the hands-on lesson, which, yeah, it was fun. But I tried to incorporate discussion as a way to alleviate.
That almost needs another name, really. In a sense, it's not right. Interesting.
Yeah.
I'm wondering if the new curriculum is the STEELS curriculum, right? Have you
Yes.
gotten guidance
Yeah,
from
so
the IU or intermediate unit or from somebody from the state?
my mentor is actually works with different people who work with talking about the new standards and developing different lessons. We actually incorporated the STEEL standards, even though it's not going to be until the next school year. So we've been working with every lesson. We kind of been working from scratch. We've been using 𝐻𝐸 I don't know if you're familiar with it, but they do incorporate all the new STEEL standards, and we've been using those lessons and trying to find ways to incorporate them in the classroom.
Is your impression that your mentor views STEELS as an opportunity to do actually a better job with their environmental and earth science?
Oh yeah, we're actually going to liaison network next week or in 2 weeks, and we're going to kind of talk about different types of lessons that we can do for the environmental portion. Any other questions?
Thank you so much.
Right, our next presenter will be Alexa Pechulis. Alexa will be speaking on using diatom abundance and diversity to understand the water quality of a suburban neighborhood stream.
For my research, I was researching water quality in Marsh Run. Marsh Run is a small headwater stream in Louisiana, Pennsylvania. This stream consists of multiple smaller stream tributaries that are possibly being affected by pollutants infiltrating the freshwater stream system. This stream drains an area of about 2.5 square miles, and the stream tends to flow about ankle to knee deep during dry weather periods. But when we have storm events, we see the stream begin to flow out of banks and into neighborhoods. And Indiana tends to have a higher than average precipitation level. So floods in this area, even if they're small, they're pretty hard for us to forecast and prepare for. The stream overflows often due to runoff, and this is caused by excessive rainfall and especially the lack of infiltration on the hill that Indiana Area High School stands on, as well as the impermeable surfaces nearby like rooftops, sidewalks, and roads. And then this rain does not get a chance to infiltrate the hill and instead does not get to recharge the groundwater. So all of this water turns into runoff. This runoff moves down the hill and into the Chevy Chase Heights neighborhood, where it then reaches gutters and storm drains, and then finally passes through pipes as quick as possible. And in these pipes, the water picks up pollutants. And then the pipes are trying to get the water out of urban areas as quick as possible. So all of the water that is coming from the pipes into Marsh Run is moving as quick as possible as well. And then roads and yards in the lower elevated neighborhoods are often flooded by the excessive water. This makes it a lot harder for any vehicles to pass through, especially for people to get to work. Some basements have been flooded, and that just worsens the water quality a lot more, because when the water makes its way into these basements, it picks up a lot of household pollutants such as household cleaners and also paint. And then all of that water from the basement gets drained right into Marsh Run. Then I grabbed both of these pictures from the Marsh Run flooding Facebook page. And this is a Facebook page that allows residents to periodically upload pictures of flooding, and this made it a lot more helpful for us to see exactly how bad it gets. Even though this was in 2017, it still does get comparatively pretty bad. And then why did we choose diatoms? Well, diatoms are very helpful indicators for things like pollution and especially organic pollution. Any shifts in nutrient levels and especially pH levels can tell us if there's been a shift in any ecosystem conditions, as well as any change in species or quantity of species can reveal any shifts in ecosystem conditions as well. And then what are diatoms? Diatoms are single-celled microscopic organisms and they form the base of the food web. So any small change that affects the diatoms will likely reflect within the rest of the food web as well. And they also use sunlight for photosynthesis. And their main role is to cycle nutrients within the stream, but they also take carbon dioxide from the atmosphere and produce oxygen as well. They have clear shells called frostules, and this enables us to better easily see internal structures of diatoms, as well as the shells have small openings that allow nutrients and water to pass through. And then, as you can see in the Dinosaur, that is my site that I was specifically looking at, and it's surrounded by residential areas, so more of a suburban site. And towards the top left of the star, that is where high school is located. And you can see on the map, the Pechulis Heights area. And then the blue star represents Austin Konopka's agricultural site. Myself, Dr. Katie Farnsworth, and Austin went out to both of these stream outlet sites, and our main goal was to take water and sediment samples. And then in order to preserve these diatom samples, we wanted to freeze them after we labeled them. And then as soon as we thawed these samples, we were very eager to look at them under the microscope, but we didn't realize that since they're still alive, these diatoms will still be moving. So every time we tried to focus on a diatom, it would jump off the screen. And it was also a lot harder to identify any of the diatoms because there was a lot of organic matter that was covering the internal structure. And when you get to see the internal structure, that tells you a lot more about which possible diatom it would be. And then in order to basically kill the diatoms and remove organic material, we allowed the settled samples to air dry, and then we mixed the samples with hydrogen peroxide. This enabled us to get a clearer view under the microscope as well. And then in order to prepare for analysis under the microscope, we glued these samples to slides. And since the optical adhesive just stays in the middle of the slide, we wanted to spread it across the whole slide so that we could see the entire sample. So we put each slide on a hot plate, and that enabled the adhesive to spread across the whole sample. And then as soon as that was done, we put each slide under the UV light to cure the adhesive so that these slides would not be moving under the microscope as well. And then in order to compare results from each site based off their surroundings, we calculated the 6 highest diatom values. We did that by totaling up each diatom genera and dividing that by the total diatom genera captured at the site, which was 224 diatoms. Our highest diatom quantity was 𝐿 that accounted for about 40%. 𝐿 is a more tolerant diatom. It tends to thrive in moderate to high nutrient levels, and it's usually present in still clear waters, so any type of lake environments. And you can see in the first picture, it tends to present itself as chains, where each one is an individual diatom. However, we also saw 𝐿 a lot in pairs as well. Then 𝐼𝐥𝐤 was our second highest diatom quantity captured. This is more of a common adaptable diatom, so it can adapt to most conditions regardless of nutrient levels or pollution. However, it's a little bit more sensitive to pH and it prefers specific pH ranges. So if there is a sudden absence of 𝐼𝐥𝐤 or a sudden decrease, it is safe to assume that there's been a shift in the ecosystem conditions as well. Then 𝐚𝐴, this accounts for about 12%. It's more of a rare diatom and it's usually in areas that are prone to drying, so seasonal streams or streams that have extreme moisture fluctuations as well. And these diatoms tend to form with cells forming in colonies. So each of these is one diatom. There's about 26 in this picture total. 𝐿𝐴 accounts for about 6% of diatoms we capture. And this is a really diverse diatom in context to shape, as you can see. And it usually has more of a club-shaped outline, which better enabled us to identify it from the navicula, because those look very similar with the thick central sternum. And although some diatoms tend to move freely throughout the water, this diatom tends to settle to the bottom and attach itself to any rocks or plants. Tabularia, we accounted for about 3%. This is more of an uncommon diatom, and it tends to thrive in areas that have higher salinity levels as well. This is another diatom that tended to show up in pairs under the microscope as well. And 𝐚𝐡𝐞 is our last highest diatom quantity captured, and we accounted for about 2%. This diatom is more tolerant to polluted areas and actually thrives in streams that are organically polluted, and especially waters that have higher nutrient levels as well. And we also captured smaller amounts, about less than 1%, of unusual or rare diatoms, like this 𝐉𝐵𝐻. Obviously, it's very distinct by its shape when you look at it under the microscope. And it's also pretty comparable to our tabularia, as it's also a high salinity diatom that is tolerant. We also captured less than 1% of �𝐼𝐬. This diatom tends to take on more of a distinctive S shape, as you can see. And this diatom prefers muddy areas, so anywhere where finer sediment would reside, like at the bottom of streams. And like 𝐿𝐴, this diatom also has higher nutrient levels as well. And �𝐴 suggests somewhat clean water, so maybe like ecosystem conditions are returning back to normal over time. And this diatom also attaches itself to rocks and plants as well. And then right here, this is not a diatom. Sorry to burst your bubble. It is an air bubble. And then overall, the diatom and air we captured, it suggests moderate nutrient levels and also moderate pollution. And this could possibly be due to road salt infiltrating the freshwater stream system, or possibly fertilizers that people are using on their yards. And overall, these diatoms seem to be pretty tolerant to these conditions, and it seems like they adapt pretty well. But we do wonder if we did take these samples during the beginning of fall, so around September. We do wonder if we took them at the end of winter, like in March, would we have higher quantities of higher salinity diatoms like the tabularia, or a lot more 𝐉𝐵𝐻 too. And then for future research, this first look at the water quality in Marsh Run could help future students if they wanted to investigate maybe the impacts downstream. And I did also want to take a moment to thank Dr. Katie Farnsworth and Dr. Adriana for helping me complete this research. Questions?
Did you notice any difference between you took two different stream samples? Was there
Yes,
any difference
we did.
between those two?
Austin was looking at the agricultural site, and although there wasn't a huge difference, but it was a little bit noticeable, especially with the outliers and diatoms. Like his site did not have the his site had the 𝐉𝐻, but it did not have the 𝐼𝐬, and it also did not have the 𝐉𝐵𝐻. So although it had very similar and comparable rates of things like navicula, his site had 25%, my site had 26%. Overall, they're very comparable, but there were a lot of outliers, and that's possibly due to the fertilizers coming from the agricultural surroundings.
I'm curious about the Facebook page, because I'm a big Snap page user, as everybody knows. So, is that like a crowdsourced way for the community to kind of collect information about the watershed health. It's really cool.
Yeah, that opens,
Not about the health.
yeah, it opens up kind of a discussion
Okay.
about just the stream health and flooding in general, and just ways that we could possibly get into Dinosaur to help. I know a lot of people on that Facebook are a little bit angry when they go to post something, but a lot of them are having their basements flood, they can't get to it. Their yards are completely flooded, so.
You mentioned that the diatoms that you observed and the distribution of those diatoms were representative of moderate nutrients. Does your kind of conclusion of there being moderate level of nutrients and pollution, does it seem like it's a higher level of nutrients than would naturally occur outside of the city? Is there like a comparison, I guess, that you could make between
Yeah,
those?
so looking at the specific diatom genera we captured, a lot of them tended to be moderate to high nutrient levels instead of low to moderate nutrient levels. So almost all of them we captured the toxic quantities. Each one was moderate to high nutrient levels, which comparable to a regular stream would not have as high of nutrient levels. So we think that's impossible to the stormwater management in this area.
Thank you.
Great, thanks.
All right, I think we're continuing along this topic, and please come on up, set yourself up. Our next presenter is Austin Konopka. He will be speaking on using diatom abundance and diversity to understand water quality of a rural suburban interface. Take it away, Austin.
So I just wanted to start off by briefly explaining how we came upon doing this research. And that was back in our 470 class where Dr. Warnock suggested someone should do something with algae or diatoms. And I didn't know what a diatom was at first. So I did some research, and I do have a minor in biology, so I thought it would be perfect. And so yeah, Alexa and I are also the first ones in Indiana to do so. So I thought that was pretty cool too. So we all know how important water is in our lives. For example, humans need it to live. So the average American uses about 1,500 gallons per day, and that includes virtual water. So what is virtual water? That's if you use a product that needed water in order to manufacture it. So besides virtual water, we use about 80 gallons per day, which is still a lot. Environmentally, it's also so important for life. It helps maintain, climate and everything with the water cycle. And economically, like I mentioned, whether it's being used to manufacture a product or a source of energy. And so I included these pictures. The one is a map showing the watersheds, as you've seen, and we're going to be focusing on Marsh Run. And then I took this picture, which is part of Marsh Run, that we took some of our samples from. And so here I have a satellite image showing my portion of where I took the samples. And as you can see, the rural agricultural suburban interface is where I was. So with that, and also these baseball fields, we can assume those are fertilized quite often. So with that and the runoff coming from that way, we can assume there's going to be an increased salinity levels from that. And so that can be due to multiple things. So like I said, runoff from fertilizer and nutrients, things like that, excess evaporation, road salt runoff, and even just simple land use changes like development. So when I'm talking about salinity, fresh water has a range from 0 to 4 parts per thousand salinity. In comparison, oceans have around 35 parts per thousand, so there's a big difference. I just kind of wanted to point that out. And so what is a diatom? A single cell form of algae, basically. Like Alexa mentioned, they produce 20 to 30% of the oxygen in the air that we breathe. This is through a process called carbon fixation, where they take the carbon dioxide from the atmosphere, turn it into organic carbon and oxygen. And that organic carbon also allows them to feed entire food webs within their ecosystem. So there's about 2 million species, making them very diverse. They're also bioindicators since this research, meaning they can indicate the qualities of their environment simply just by living there. So, and how that works is so just about every species requires such certain conditions in order to thrive. So whether it's like a certain pH, salinity, or temperature, and all the variations in between that. And that's actually a picture from the microscope samples that we did. And so like Alexa mentioned, we took our samples back in September 2024. And we took them from the surface of the stream bed, surface of the rocks, like these sediments like boulders, and even plants, obviously submerged in the water. And once we took this, we froze them to keep them preserved until we were ready. And once we were ready, we just simply thawed them, put them in these jars, added hydrogen peroxide to get rid of that unwanted organic matter. And then we were able to prep the slides with an optical adhesive, and that just kept them in place, like Alex mentioned, with the hot plate and then the UV light setting them in place. And so once we were able to look at them in the microscope, we were able to identify 224 individual diatoms that included 17 genera. And so with that total, I took the top 90%, which included 6 genera. And I did that because after like, if there's like 0.1%, it's not really relevant to abundance. So that included the 𝐼𝐺𝐻, Navicula, Tabularia, 𝐜𝐵𝐻, 𝐻𝐼𝐻, and 𝐵𝐻. So pretty similar to Alexa's, but there are a couple that are different. So now we're going to go through them individually from most abundant to least abundant, and see what they indicate. So starting with the 𝐼𝐺𝐻, you can see they form those band-like chains. So it's a bunch of individual ones just hanging out. And they're actually one of the ones that don't require such specific conditions. Except when they're found, they're usually found in areas of still water, which is interesting, and I'll come back to later. And then the Navicula, also like the 𝐼𝐺𝐻, they can tolerate most conditions, just not heavy metals or pH. There's the Navicula. So now we're going to get into the ones that do require specific conditions, starting with the Tabularia, which if you can tell, it's this big dark one right there. They're considered rare, meaning they're not found often. But when they are found in high salinity freshwaters. So there's our first indication of that, what we were expecting. And here are the pictures showing the 𝐼𝐻𝐿𝐵𝐻, which you've seen before, and the 𝐻𝐼𝐻 on top. So the 𝐼𝐻𝐿𝐵𝐻 is like the 𝐼𝐻. They form those colonies, also found in areas of still water, specifically where there's excessive evaporation. And then the 𝐻𝐼𝐻 also found in nutrient-rich and high salinity freshwater. So we're starting to see that pattern. And then lastly, the 𝐿𝐵𝐻, which is also found in nutrient-rich and high salinity waters. So you guys can see all these little like dots, right? Those are called frustrals. And they help us identify whenever, because some of the diatoms look so similar, like the genera. So let me get that. So the 𝐼𝐻, if you were to turn this picture like 90 degrees or like look at it this way, you would see circles because they're like cylinders. So like when you're moving under the microscope, they change like with the angles and stuff. So those frustrals that you can see, their intricate patterns and shapes help indicate or identify. And so I just wanted to show this table showing the actual numbers of percentages and talk about it a little more. So the 𝐼𝐻 and Navicula being the most abundant was no like shock because they don't require such specific conditions. So they're able to thrive under subtle changes depending. The 𝐼𝐻𝐞 and 𝐼𝐻 being found in still water that could be, the streams flows really slow. Also, there's a retention pond of the stream, so they could be coming from there. And then the rest were what we were expecting, nutrient rich, high salinity. And just to show you the satellite image again, with those results and all these land use, those baseball fields, fertilizer, runoff in there, and it's right there. We can assume that this high salinity is from agricultural runoff, fertilizer, nutrients, and also excessive evaporation, like the 𝐚𝐡𝐞𝐽 suggested. Which makes sense because these were taken in September when it was warm out and summer just happened, it was super hot. And I did want to mention that further research can be done. What I would do is take samples from each watershed throughout the year. That would just give us a bigger picture of what's going on throughout Indiana, not just Marsh Run, also throughout the year and see what changes. And to take it a step further, I would figure out the species, not just genera. That will also give us a more detailed result. And I just wanted to thank Dr. Burnsworth and whatnot for their advice and help throughout this whole research and project. I got those pictures from IUP.
Kind of a philosophical question, but why use diatoms instead of just measuring pH and
Right.
nutrient levels? And did you do any of that to sort of
Compare.
ground truth?
I kind of just never thought of, like, I never heard of this and I thought it was interesting and I wanted to do it, I guess. And I did read somewhere that it was like cost efficient, but I don't know how accurate that is because you need like a microscope. And I'm not really sure the cost of doing it regularly, but. Other questions?
Which one is your favorite?
This one, Barbie. It also has the shape of a Barbie, I think.
So it seems like this is a sort of a census at this point, like you're setting the stage for an understanding. I was curious, you mentioned some of the habitats that are, the niches are kind of narrow. I imagine with flash flooding, some of them end up at times in less than optimal places, and figuring out like the significance of that through time would take a lot of, maybe some time series, you know.
For sure, yeah, like it could be over time.
Yeah. Yeah.
I did, but now I don't remember. Okay, you were focusing on the diatoms that were most prevalent. You said the top 90%, those genera that you were focusing on, and you sort of disregarded those with, I forget what percentage you said, anything smaller,
Like 0.1%.
anything less than 0.1. Could you expand upon that? Like, why do you ignore the ones that are less than 0.1 if there are different genera that are in the streams? Could they not be bioindicators, or is there truly just not enough to? Can you just expand on that?
Yeah, so I guess since there's not so much of them and we're looking at abundance, it's just irrelevant to. I mean, I guess maybe, water quality can change and things like that, so maybe if that's just not what the water quality is right now, like maybe they all die off. You know what I mean? Or maybe it's changing to what they like they're starting to come around. I guess it's just not what it is right now, you know what I mean?
Understand.
I don't bother below 3%.
Okay.
Any other questions?
Okay.
You all took my warning about being back in your seats before 9:30 seriously. That never happens. That doesn't happen at meetings with faculty or administrators. That doesn't happen with students in class when classes begin, supposed to begin. Thank you. From the bottom of my heart, thank you. All right, our next presenter. As you may have noticed, there's been a bit of a theme here this morning for the initial presentations, kind of focusing around hydrology. We have one more of those, and then we're going to get a little bit more miscellaneous, talking about acid mine drainage and some paleontology, and then we're going to come back to diatoms later on in the final session, I think. So our next presenter is Hope Burbank. She's eagerly waiting here. She will be speaking on establishing a baseline of stream characteristics in Indiana County, PA, leveraging community connections. That's all yours, Hope.
Hello, everybody. My name is Hope. I want to thank you all for coming out today. I've been working with Dr. Katie Farnsworth as well as the Evergreen Conservancy to this project. And if you don't know about the Evergreen Conservancy, they're just a local conservancy group that really focus on the health of our environment and educating the public about that. So as a little bit of a background, I'm going to start off giving some historical context of this region, as well as, where this project started off from. So the streams of Indiana County have been very significantly impacted by resource extraction for about the past century. And this picture here is an example from Blackwood Creek. As you can see, that one color in the stream, we don't like that. That's from acid mine drainage. And if you live in this area for any amount of time and try going out to the woods or on a hike, you're going to see something that looks like this. And this is one of the big things that the Evergreen Conservancy does focus on. So one of the examples of this is their Tanoma Creek Acid Treatment Center. And this works into their two main goals, which is restoration and education. So this is one of their big restoration projects that they also use to educate the public. And by building this, they are slowly leaching out that acid mine drainage and other pollutant sources from the stream. So the Evergreen Conservancy has been conducting stream monitoring since about 2011. And they've been doing so using stream data loggers. And these stream data loggers have been placed in about 36 streams across the county, and they've been recording data every 15 to 30 minutes. So as you can imagine, we have about 36 streams. We only looked at 34 of them due to data reasons. Some of them only had a couple months of data collection, which just wasn't good for our purposes. But with this, they are recording temperature in Celsius, water level in centimeters, and conductivity in microsiemens, which we converted to total dissolved solids in milligrams per liter. We have many advantages to working with our local community groups, such as we have some local experts, and because it is mainly a volunteer network, these people are being told that you have to go out there and do this for a paycheck. They're doing what they would like to be doing, and they're more motivated to do so because it's volunteer work. This also creates a lot of community support for the local environment, and with them educating the public, it just helps create that nice community support. And if you become a member of the Evergreen Conservancy, you actually get like certain discounts in certain restaurants around town, so kind of creates that incentive to join and be a part of your local environment. There's also some challenges working with community groups. One of the examples I have pictured here is something that can be a challenge when they are installing these stream data loggers. So not everybody is a professional that are these volunteers. So one of the things we might see with these stream data loggers is one being placed in an area of low flow for the stream and another being placed in an area of high flow for the stream. So if one is placed in an area of low flow for the stream, we might see decreased TDS levels and increased level measurements. But if it's placed in an area of high flow, we might see increased TDS measurements with decreased level measurements. This is just something we kept in mind when we were looking forward into our baseline analysis. So we have analyzed the data that we have received from all 34 streams, again, excluding a couple of them just due to some data inconsistencies with only a few months of data. So our first step in all of this process was to do a quality control and then atmospheric pressure correction and a baseline analysis as well. So the very bulk of this project was done using Python coding because we had 34 streams worth of data, which many of which have been recording for about 11 or 12 years or so. And they've been recording that data every 15 to 30 minutes. So we did have thousands of data points and we couldn't look through that by hand. So if you look at this graph on the screen, I'm going to be focusing mainly on Big Yellow Creek, shown in the red or the pink there. And I'm going to be mainly focusing on Big Yellow Creek as it was a good proxy as to what many of the other streams showed similar patterns for in the analysis. And as you can see, we have a good duration of data from Big Yellow Creek. So we have that data from about 2011 to about 2023. As opposed to a location like Harney Run, where we only have data from 2011 to 2015. Some of these other sites also only have data for a couple years, up to a few years, so we just keep that in mind when we were looking at our analysis. So moving on to the quality control and Python coding. So our quality control and processing of the data was done by coding Python scripts to automate our steps. So as you can see from the set of 3 panels on the left here, that is our data that we're starting off with after this first step. So this first step is telling our code to get rid of any temperature values that are less than -50 or above 50 degrees Celsius. And if our level measurements are below 0 or above 500 centimeters, to get rid of those values. And if our total dissolved solids values are less than 0 or above than 3,000 milligrams per liter, we tell our code to exclude those values. As we can determine that these are impossible values to get in these streams. And they're very, like, if you go back and we look at the data by hand, we can see it's just a few recordings that reach these extreme measurements. And we can tell maybe the stream data logger was dislodged or it was disrupted, something happened with it that we know is not correct. So our step 2 was to calculate our Z values or Z-scores to remove more outliers. So as you can see from the first set of panels to the second set of panels on the left here, those values that I circled in red do go away with our calculation of Z-scores. So a Z-score is calculated by taking the mean of our data set and subtracting a certain data point from that, and then dividing that by the amount of standard deviations that specific point is from the average. And then our third step was to calculate our rolling median or rolling average. And this wasn't a significant step in the quality control process, but it did get rid of a few more values, so it made our data just that much, little bit more controlled and better to work with. And our last step of this quality control process was to do a barometric correction. So our water level values were also post-processed to remove atmospheric pressure from the measurements. So in the water level measurements we're given, it gives us a value that we don't want. So it gives us a value of our water depth plus our atmospheric pressure. So it gives us the value represented by the white arrow. But we only want the data that we see from the red, that would give us the red arrow, just the water depth measurement. So we do this by looking at the atmospheric pressure data we have from the Indiana airports and from the Pittsburgh International Airports, where we do not have data from the Indiana airport. Moving forward into a baseline analysis. So results from the 34 streams do show similar patterns. And for this, I'm going to be mainly focusing on 𝐜𝐵𝐿 Creek, as I mentioned earlier, as it's a good proxy for what a lot of the other streams show. So we do have expected seasonal patterns that we see in our water temperature. So for the next couple slides, they're going to be formatted this way. And the big graph on the left is always going to be from 𝐜𝐵𝐿 Creek. And then the 2 other graphs are going to be from supplemental streams or creeks to show some more examples. So with the big graph on the left, that green line on top is going to be our average maximum values. And the blue is going to be our average values. And the purple is going to be our average minimum values. And then on these graphs here, the gray in the background is going to be the data that we see from every stream that we have, while the blue is just going to highlight that specific stream. So we do see what we expect to see with temperature readings, increased temperature readings in the summer and then decreased in the winter. And we see that for every single stream except 𝐻𝐻 Run. 𝐻𝐻 Run shows this little bit of a dip in the summer months, and we're not sure why that is. Our year-round rainfall results in steady water levels. So water level does vary from stream to stream in Indiana County, but they all show similar patterns of The water levels that they start out with in the year, they end within the year, even though there are dramatic events that influence this level throughout the year with how much rain we get. It does remain steady throughout the year, but this does show the flashy nature of our streams from all the spikes we see. And then the total dissolved solids values, they vary the most greatly from stream to stream. This is because this could be because of where it's located to an agricultural field or a road, or where it's located to an acid mine drainage site. So in Backyard Creek, we see this interesting spike in the late February, early March months. We think might be from road salt runoff, just due to the time period that would be more realistic outcome. And then in the late summer, early fall months, we see this gradual increase that slowly goes back down, and we think that might be from biological activity in the summer months and or algae blooms. So we do have lots of unanswered questions, as I mentioned earlier. Like we have that dip in the temperature months, in the summer months with Kesna Run. We're not sure why that is. We also have, we have hypothesis on why some of the TDS levels can be as high as they are, but we didn't do any chemical analysis, so we cannot be, conclusive on those. So this makes a lot of room for baseline. It's a baseline for future potential projects where students could answer those questions that we've created. We're also going to be giving this data back to the Evergreen Conservancy, so they can continue to educate the public and help understand the health of our local streams in Indiana County. Some other projects that can be done moving forward with this data is creating rating curve calculations and stream cross sections, and then using Mandy's equation shown at the bottom to calculate discharge values as well. But that is all I have for now. So if there's any questions, I can take them now. And I urge you guys to scan this QR code if you're interested. This links you to the website. You can sign up to volunteer or be a member if you'd like.
You have time for a question or two.
Oh, nice job. I have a question. With the data loggers and, are those all does the data just automatically go to a database, or do they have to be monitored all by those volunteers individually? And do those volunteers, do they have the ability to do the coding and the processing and the Python stuff that you do, or is it basically just data collection from them?
Yeah, so the stream data loggers do just go to a database that they have access to, but they do need to go out there sometimes and monitor them. Because especially like during COVID or something, a lot of them, if they went down, people would have to go back out there to fix them, but especially during COVID, people weren't doing that. That's where a lot of our quality control came in for, time periods in that range. What was the second part of it?
Yeah, the Python coding, that seems like it would take a good bit of training to be able to do that. Is that something those volunteers can collaborate with, or does that have to be done basically professionally by you guys?
Yeah, so our Python code is set up right now. All you have to do is input the stream name as a text file, and then it gives you the data you need.
Okay.
So as long as if they have access to our code and they know that they just need to input that value there, that's all they need.
Okay, cool. Thank you.
Yeah.
I mean, it's really great, and I imagine if you could, maybe you're angling to get some of this published or get it out there in some way, shape, or form, because the data sets and this sort of analysis is fodder for people to write more growing greener grants and getting more funding, and watersheds could make the justification that these data loggers are well worth the investment because they show us things that we would have missed. Is that something is that a priority for you? Because, like, I know you've got your next chapter already lined up, but get this stuff out there published in some way, shape, or form.
Yeah, we have talked about it. I think it's something that might happen over the summer, but it's definitely something we've spoken about doing. But yeah, we're gonna really be working at least, if we can't get anything published, we're gonna be making this public somewhere. So whether it's like on Katie's website or on a different website, and we're gonna be giving it to the Evergreen Conservancy as well, so they can also make that public as well.
I think Priscilla had a question, and then we'll go to the next one.
Okay, so
The connection interests me. Is this senior citizens or also little kids? What is the age range?
So like the people they're educating or?
Yes.
They do, so they do public education, so whoever wants to come can. They do specific events a lot of time, like during the summer for groups of kids. But it is mostly just open to the public, especially like their meetings that they do, that's open to anybody. That's a member for anybody in the public.
So did you meet with these people?
I've met with them before, yes. Cindy Rogers is like the head of Evergreen Conservancy, who I've met with a few times.
All right, we need to move on to our next presentation. Thank you, Hope.
Thank you.
All right, our next presenter, let's swing forward, is Zach Stuart. I'm speaking on Tanoma acid mine drainage analysis.
Morning, guys. Just want to thank you guys for coming. So we'll start by just giving ourselves a little bit of background on where Tanoma actually is. So in regards to Indiana, it is northeast of Indiana, approximately 9 miles or so. It's about a 15-minute drive. If you're more local to the Indiana area, say you're from Clymer, so just about northwest, not very far. It's just south of the village Tanoma, where it gets its name. It runs along Crooked Creek, which flows into the 𝐚𝐿𝐴𝐺𝐸 River eventually. But Crooked Creek is its own watershed, and that's exactly what this system affects. So in the 1950s and 60s was the Tanoma Mine Complex was operated under the Tanoma Mining Company. It was operated in the lower Freeport seam. This mine was pulled from Rosebud Mining Archive, where I work, and this mine map is their lower Freeport seam, and it is approximately 3,200 acres in size. I have read reports that this is a little bit more complex than just one complex. I've heard that it's actually 2 or 3 that are so intertwined together that is what makes up the one complex. So I've seen reports saying that this number gets up to as high as 4,500 acres in size. So it's a rather large complex. And our site is right here on that yellow dot, which again rides right along Crooked Creek, so it can heavily affect Crooked Creek. So Crooked Creek is affected basically just how this stream was. So on the left, you have a picture of a stream that is being affected by acid mine drainage without any treatment. So you see that orange discoloration, you see the sediment in there. You can assume that aquatic life has taken a downturn because it is so murky and dirty and eroded. On the right side, you have that same creek that has been treated. So now it looks clear. The heavy metals have been removed. I'm assuming that the pH has been fixed. It just looks better, and overall it's better stream quality. So to achieve that remediation, there's a couple methods. They fall under 2 categories. You got your active and your passive treatment. On your left, you have an example of active treatment, which overall active treatment is much faster than passive, but it is much more costly. It uses the addition of chemicals, it uses machinery, it uses basically very costly methods that just wouldn't take a lot of time, but it is what it is. When on the other side, you have passive, which is, it takes much longer to treat something, but it costs less money. So that is your retention ponds, your wetlands, and your Tanoma complex, or your treatment center, I should say. So the goal when treating acid mine drainage is to return the water quality back to what it was. So by doing that, you want to drop out your heavy metals and you want to reestablish your pH. So, like I said, Tanoma is a passive system. It is a 10-pond passive treatment system with wetlands and limestone beds throughout. The limestone beds are there to help reestablish the pH back to neutral settings, because once those pHs are back to neutral settings, that's when your heavy metals can drop out and it becomes much easier. Another goal of the Tanoma system is to increase aeration, because along with aeration and the reestablished pH, you can really get those heavy metals to drop out of the system well. And Tanoma does that very well. So a little bit of background, this is Crooked Creek that runs along the site right here. Before Tanoma was put in 2001, there were 3 boreholes right upstream from the site, right down here, that were tapped, and they were just depositing affected mine water right into Crooked Creek. So what DEP did is they went in, they plugged those 3 holes, and then when putting in this system, they drilled 3 new boreholes at the system to redirect the water into the system. The water flows out of those boreholes at about 2,500 gallons per minute, which is roughly about 3.6 million gallons of water a day. So it is quite a lot of water going through that system. Once it enters this first pond, that's really where we want most of the work to happen. So they put a lot of work and effort into advancing this first pond so that the other 9 do not have to work as hard. In the first pond, you have the floor lined with limestone, like I said, and you also have what are called baffles. If you go there, there are these large yellow beam looking things that go across the top of the water. Well, there are curtains that fall down underneath those beams, and about a foot down on those curtains, there are rectangular windows, and they go all the way across the beam to allow for even flow of water to go through those areas at that time. If the water isn't flowing through that window in the curtain, it just ends up circulating and increasing that retention time, so it exactly falls right under our goals like we want it to. Another large advantage of Tanoma is their trompe system. Their trompe system is a technology from the 17th century. It has no moving parts, and it was installed around 2015, and it takes advantage of the system itself. So as the water leaves the system at Pond 10 to be returned back into Crooked Creek, it falls over a drop, creating compressed air. And that compressed air is then pumped through air lines back to Pond 1. And then it is pumped into Pond 1 through diffusers and bubblers. So if you ever go, say, like to the mall and you see a fountain bubbling, it's because it has a diffuser in it that is getting oxygen pumped into it. Same idea here at Tanoma. I believe they have 20 or 25 or so diffusers at the bottom of that first pond. So they're really trying to get oxygen into that system to pair with that retention time to really get that drop out. So with that in mind, Dr. Warnock and I went to Tanoma, and we collected a sample from this Pond 1 weir. So between the first pond and the second pond, there is a weir that had sediment built up on it. So we collected our sample from that. This is our sample right here. Now, the reason we collected our sample from that weir is because when I was taking my PVC pipe and I was trying to core the pond itself, as I would pull the pipe up, the suction from the water would pull the sediment back out of the core. So we had to choose an alternate route. So instead of the sediment depositing vertically, we went to the weir where it would deposit horizontally. So same deal. So once we obtained the sample, we brought it back to Indiana, we froze it, and then brought it out of the freezer and let it dry, and then prepped it for sample. So again, that sample was only 2 or 3 inches, but to increase the amount of testing that we could do, I poured it out onto the paper, and I poured it out into about a foot increment, just so I can get as many samples as possible. The side on the left was the side that was exposed to water, whereas the side on the right would have been the side that was on the wood of the weir. So we then ran it through the SEM. We used X-ray diffraction to basically see what that sediment was made up of elementally. And here's some results. So overall, the results were very consistent. We saw the same peaks throughout. I just chose these 4 because there was slight variation in each, but every sample of the 15 or so that we collected had this carbon, oxygen, and iron peak there, which is basically exactly what we were expecting. But there were some other variations, such as the aluminum here, your manganese here, you had a sulfur down there, and also common in all samples was this little spike of calcium right here. Now, some of those findings are expected, like the carbon, iron, oxygen, and calcium. We expected those. The carbon, just because, again, it's an aqueous environment, so I'm sure there are some algae present, maybe some diatoms. The wetland plants are present as well, so carbon is going to be there. Again, the oxygen, the main idea of the system is to introduce as much oxygen as possible, so we're not very surprised to see the oxygen in the system as well. And iron is the most common heavy metal in acid mine drainage. So again, not surprised to see that. Now, there are some other things in there, the variations that we saw, that could be explained just by the rock present at Tanoma. So your aluminums, I believe that this could be due to the presence of kimberlite, or so kimberlite is a rock which is made up of aluminosilicate, which is a part of the mica family, so that has your aluminums in it, which I believe that could probably describe it. Pyrite is present in coal often, and pyrite is made up of FeS2, so that would introduce your sulfurs, and again, that would be your large contributor to iron being present in the mine. So again, nothing too crazy. Your manganese is also another element that could substitute into your mineral formulas in the present lithology at Tanoma. So again, nothing too shocking, but it was interesting to see that variation. So overall, the system appears to be pulling out those heavy metals. Even though, again, we did only test that one site, but it is designed ideally to leach out these heavy metals and treat that acid mine drainage. Now, with that being said, I do think that there could be further research done specifically at Tanoma. Some ideas I have, instead of me testing right here at this weir, I think maybe test at every pond to see what pond is doing the most work, to see possibly to see how to also alter the system so one pond or one part of the system doesn't have to work so hard. I'd be curious to see what that result yields. I'd also be curious to see a test at the start of the system versus directly at the end of the system, just to see overall how effective it is, not specified on one specific area. And I think something else that might be interesting too is test upstream of Crooked Creek before you hit the system, and then test downstream of Crooked Creek after you hit the system, just to see if life upstream is healthier or not as healthy, say, as area downstream of the Crooked Creek. And I don't have a thank you slide, but I would like to take a moment to thank Dr. Warnock for giving me a hand and visiting this site with me, and just basically giving me somebody to bounce ideas off of too. So it was really helpful. Thank you.
We have enough time for a question or two, not a ton of time this time around.
Okay, so if I understood you, as soon as you bring down the pH, the heavy metals fall out. So how do you, in this passive way, how do you bring down the pH? Is it just time? You just wait and it goes down?
So underlying every one of these pond systems is limestone beds, calcium carbonate beds. And as we all know, limestone helps reestablish that pH and bring it back to more of a base level. So with that, that's how you're gonna be.
So you just wait.
Yeah, it's very dependent on time and exposure to the system. So with, like I said earlier, with the baffles, that really just helps that water stay. So these go all the way down to the ground. So basically they have to snake their way through these ponds. So the longer that they can stay in those ponds exposed to that limestone floor, that's gonna be able to.
So is it like 10 years?
I don't know that exact number off my head. Completely honest with you.
Zach, I just wanted to say, I've been walking by these things my whole life living in southwestern PA, and that was such a great explanation of how it works and what it's doing, so.
Thank you.
Thank you for that, and just out of curiosity, are you gonna be doing that kind of work with Rosebud?
No, I'm actually a geologist for Rosebud, so I'm basically gonna be doing a lot of mapping and a lot of analysis of like the coal and
Okay.
basically just trying to keep us on track of the coal and keep our
Interesting.
company.
Well done.
That's really it.
I can tell us exactly how much pyrite is in that. The source. Okay, our next presenter will be Sam Jubin. We're gonna transition a little bit here. His topic is environmental change through time as identified through the rock record at Cleveland-Lloyd Dinosaur Quarry.
Alright, everybody. So just to get the main goals of my research, I wanted to see what the environment was like in the past and what sort of area we were depositing in. The main reason I was interested in doing this is because I believe it's a very powerful thing to be able to see into the past of what kind of environment is or was it in the area. So just some baseline stuff. This area that I'm going into is part of the Morrison Formation. It's this huge depositional basement that reaches up into Canada and as far south as New Mexico. The section I'm working in is around 148 million years old, so that puts us in the Upper Jurassic. And this is just a strat column to see sort of where the scale we're looking at. This is where I'm looking at. CLDQ stands for Cleveland-Lloyd Dinosaur Quarry. And this is a section starting at the Somerville Formation. We're starting up here. And so the overall section is about 60 meters in height. So zooming in even further, Cleveland-Lloyd Dinosaur Quarry is in Utah, specifically in Emory County. And in this very rural area right here by the towns of Cleveland and Elmo. Each of those towns have a population of less than 1,000 people combined. So very rural, very remote, really good area to do good geology. If you wanted a ballpark of a big city, Salt Lake City is about 3 hours drive away. So this is just a Google Earth image of the actual site. The museum is right here. There's a large picnic area over here. This is where we camped out and stayed here because it's so far away from society. Over this trail, those two buildings right there, those are actually the quarry themselves where they dig out all the dinosaur bones. Over here, as well as the main section, and further along the trail that way, there's a rock walk that you can go to and see some geology, and further up that way, you can go up to Raptor Point and see the whole scope of the area. So this big red circle is the main section that I was working in and what I was looking at. Just that sort of wall and all the red and gray bits. The main stratigraphy of this section is defined by these 4 rock types. I'll be going into more detail about elemental data as well. Yeah, those are the 4 main types. And this is, so the big red circular area, this is a ground view of where it can stand. So this is mainly found here in this border area. You can kind of tell because it has this little border line on it, and a lot of those rocks show through here. And this repeats, you can find it up further here as well. This finer stuff is usually capped off right here, and it's found a little bit up here as well. This chunkier stuff, you can find it further up, and then that big chunky boulder stuff, you find it mainly at the top. So for taking images of these samples, close-up images, we needed to use the scanning electron microscope. I'll be calling it the SEM, but it's located in the room over there. And the main idea was to sort of see the surface topography as well as record the elemental data of what these rocks were made out of. So just a quick explanation to how this works is that there is a tube, that shoots electrons out of it, and basically what it does is it condenses electrons and hits the surface of the sample down here. What these electrons do is they're able to scan the sample as you move it through in and out of the microscope. And what you get, and the reason you can see the images is this process seen here. So these electrons coming in and shooting down onto the surface of the sample, those electrons interact with the atoms of the sample. And what that does is it produces secondary electrons. And those electrons shoot out of the atoms and are picked up by these detectors here. And that creates a surface image of it, of the samples. And for the elemental data, we have to use a different process. So same thing here. Primary electrons shooting into a shell and a secondary electron here. The only difference being is it shoots into the inside instead of the outer layer. So electrons like to be stable, they like to be further closer to the nucleus. So what happens is it'll jump down to a lower shell. It'll emit an X-ray. And those X-rays are characteristic of specific elements. So you get a certain energy, a very specific energy output. Those are the two main methods that we use to get an image and to describe what elements. This is just another process here called backscattering. So we didn't use this, but basically it's a primary electron. Instead, it shoots around the nucleus. It sort of rebounds around it, and that can give you images as well. So these are what the images look like. Note of the scale, these are going to be a little different for each sample. So this is 500 micrometers. You get this really flat surface on this sample. So the interpretation is that this is probably some kind of siltstone. And here is what the elemental data looks like. So most of these are mainly going to be composed of silica and oxygen, but there are some traces of other elements like aluminum, magnesium, and sometimes iron, which will be important for environmental interpretation later. And then here are the finer grained rock and the larger grained rock. These are both sandstones. And the scale here is 3 millimeters, and you get a really nice image of the sort of topography of this. So really weathered, really 𝐚𝐴𝐤. It's the same image, but there are differences in each one. They would look similar under the SEM. The only difference is this would probably be a little more porous, so you'd see more holes, and this would be more cemented, and the grains would be a lot closer together. And so the elemental data is also very similar. Very high peaks in silica and oxygen, a little bit of aluminum as well. That's why we're able to call them sandstones. And then here is our conglomerate. Called a conglomerate because they really are pebbles. And that specific picture, this rock actually came off. So what we did was we flipped it over and we took an image scan of the actual matrix of the rock. And so this scale here, 5 millimeters around, and you get this flat surface, and the elemental data sort of comes out like the siltstone, but same thing again, very high silica peaks, very high oxygen peaks, a little bit of aluminum, magnesium, sodium, and a little bit of iron as well. So, interpretations. The color of these siltstones are very important because that lets us determine the water level using iron oxides. So iron 2 oxide forms an anoxic environment, meaning that there was low oxygen. So the idea is that this was a higher water level area. And iron 3 oxide forms in richer oxygen environments, so still water, but slightly lower water level. So whenever you look at these, you can say that this was probably higher water level, and then moving upwards, it's probably lower water level, and that goes throughout the section. Structures also can tell us about the environment. This is more of the sandstones, being the finer grains and the larger grains within this. So we have these neat little crossbeds that flow through here, as well as some differences in the grain sizes. So you can see this energy level change through time. And if it was more well sorted, it'd probably be wind deposited, but since there is not great grain storage, we're probably thinking change in water flow. And this is a really good example of the conglomerates being a change in energy. So we have very low variability in grain size, and then you move up and you get very chunky sections of conglomerate moving further up. So this also is indicated. This also indicates a very high flow in energy. So to wrap up the interpretation parts of it, this section was cyclical. This was probably slightly. So the idea is that this was sort of a still water pond in the grays and reds, just varying levels of water. These sandstones right here, moving up through, probably some sort of stream, small river, and then large sandstones up top, meaning very large, big energy river coming down. And for further research for students, there's a lot of stuff to talk about in this area. So a lot of volcanics, there's plenty of ash deposits here to look at. You can get the chemistry of that and sort of interpret what was going on and what was happening at the time, sedimentation rates. So I didn't measure out any of the heights of the sections. So if you could go in and get the data for how long it took these places to lay down the sediment, that would probably help out a lot to figure out stuff about the area, tectonics. Around the same time as this was all being deposited, that was when the southwestern United States was stretching out due to faulting. And there are plenty of opportunities to dig up and look at dinosaurs, which this is a bone that we pulled out of the ground this past summer. I want to say it's about this tall. 𝐉𝐻𝐿asaurus, shoulder bone. Got it in a cast, had to take it out of the ground. It was super heavy. I think it was like 500 pounds. It was pretty massive. So thank you to John for bringing me out. Thank you to Katie for helping me with all my stuff. Thanks to Mom for coming out. Hey Dad, if you're watching the stream.
Can't believe that was our first thing to the parents. Remember that, do your talks. Yeah, any questions? We got a couple minutes. Go ahead, John.
The fine grain lithologies, I'm curious about the beam side, because the SEM has a very a spot analysis, so when you do EDS, you're getting, you know, a grain or something really small.
Yeah.
And so did you sort of do a scanning mode to try to average that and say, this looks like a siltstone with a silicon, a little aluminum, that might be, you know, micas or something like that, or?
Yeah. I imagine it was the scanning mode, so it was mainly just we would pick a spot, it would scan it, and then it would look at that specific spot, and you can move it across, focus it however much you want. So whatever level of detail that you needed.
Were they coated or environmental mode? Were they sputter coated?
I didn't do these, John.
Uncoated high vacuum.
Oh, sorry, uncoated, environmental mode, okay.
Yeah, and it's in a vacuum.
Yeah.
High vacuum is not environmental mode.
Oh, no,
Low vacuum would be more of an environment.
but it's not coated.
It would not go there. John stole my question. I was gonna ask, because there is a spectral mode where you can scan an entire area rather than do the point analyses. Most people do point analyses. There is a way to do that. For students that want to do this in the future, you can average an entire area over a period of time. That is an option. Any other questions? Since mine was stolen. Sorry. All right, well, we're out of time anyway, so we'll just move on. All right, our next presentation will be by Autumn Jones, who will speak on, that is the next one, right? Yes. Identifying the orientation and grouping of Stegosaurus vertebrate fossils.
Why did you raise your hand?
Hey, you got a good job to do that.
To further the, idea of the Cleveland-Lloyd dinosaur quarry, it is in Price, Utah, and, you can see on this map here, this is where it's located, compared to Salt Lake City. It is 150 million years old, and there's still some ideas circling around about, what the actual cause was. We can see that in this picture, like Sam was saying, these are where they dig at. You can see the terrain is very desert-like, very dry. It was first founded in the 1920s, and the digging investigating really started in 1931. So the quarry has a large deposit of Allosaurus, or theropod dinosaurs, and there's over 12,000 fossils located there. So 159 years ago, it looked drastically different. It was in the Jurassic period, so it was very lush, very had a lot of flora, and in this area there was likely water. So the dinosaurs were likely there to what is the vegetation and the water. So here is the map of some of the excavations done. This was done in 1960 and through 1990. And I will kind of explain since it is kind of a mess. So the green here is all of our Allosaurus. Like I said, there's probably like 50, I think, found or so. So we have that mass amount there. And then the orange or tan color is the 𝐚𝐼. The blue on the right-hand corner view, it is Diplosaurus, and what we'll be focusing on is the red, which is our Stegosaurus. So if this map extended a little bit more, you would see that our vertebrae were found up there by that source. And these excavations are done by, we find the fossils, you would cast them so you can transport them back to a lab, and then you would be doing cleaning and adapt. So the theory that we're going to do, or what we think of what happened to this quarry, is that it had went through periods of flooding and drowning, very high ortho quality water or abundance of water. So we can really see the flooding aspects of it because the fossils are very much in disarray, they don't have much order. And to back on that, flooded areas would scatter the fossils, and like this picture from Cleveland-Lloyd dinosaur quarry, you would see the fossils in disarray. Whether if they were going through a drought, the fossil would stay in place and would not scatter on their own. So I think to start to understand the quarry itself is to really help us understand the animals that live there, what they're doing, and understanding one, you have to understand two. So these are my three set of vertebrae. I kind of ordered them into pairs of like in order of cleaning. So over there is our less like just uncasted, not very in order. A lot of the pieces are still casted or not out of the gas. And then our third one, there's still a lot of rock on it, but we have all the main structures on it. And then our last one is probably most clean looking and gives us a really good idea of what it looks like. So I started to identify the anatomy of it. So luckily on our one vertebrae, we have a parapomposis, which is hard sometimes to find because they erode so readily. So we were lucky to have that would stick out from the base of the vertebrae, and we kind of have a little bit of the parapomposis here too. Then we have our diapophysis that would stick up on the like top of the base of the vertebrae, and then our neutral spine, which would stick straight up from the base of the vertebrae. And then we have the neutral canal. That one is, again, a lot of rocks, so you don't see the neutral canal that much on that one. But here we can see, on this one, it would be hollow, the rock is, likely there because it's hard to really always damage the various sides. And, very this, life in place, it's always in the map, the hill somewhere. You can see the neutral spine that sticks straight up. The little notes down there would probably be the diaphysis, and then the paraboscis would stick out like this. So I wanted to really start building on the idea that this is likely from the same Stegosaurus found in spaces. And so I wanted to take some measurements to see if they were likely the same size. So I took a measurement of the bases of the 3 vertebrae, and they all came out to about 9 inches. And then taking the neutral spine of the 2 that we had, the condition of we measured out to about 2 inches. I think to further the idea that this is our map here, this is the zoomed left corner of the right corner of it that you just saw. And we see that this pelvis of the Stegosaurus is there and ours are version are out there. We can either maybe research and build onto the fact that maybe this is even part of our same Stegosaurus. I think with that we can kind of start hypothesizing that these Stegosauruses were probably in the area, or our Stegosaurus was in this area because of what it provided. Like I said, it was probably a water source. It came there for it to eat something from all the vegetation, and it might have even that they might have lived readily, which we do know, but would have been in that area at the time. I also think the likelihood that these are 2 different Stegosauruses vertebrae is probably harder to prove. We have only these said, and then again our pelvis. I feel like if there was more bones in the area, that you could probably prove more that there were 2. And compared to how the deposits of the vertebrae were there, it was probably scattered around a bit because of flooding, and probably they died very soon after the flood, or died before. To really conclude, my hypothesis is that I believe that they were here because of a water source, and that it was most likely they were deposited fast. This vertebrate we have here is limestone on here, and it could be said that it is calcified flush, meaning that it was deposited rapidly from the flood. I also just want to give a big thanks to Dr. Warda for all his help for doing all the heavy lifting of the vertebrae and dating plating. So thank you for that.
We have time for a few questions. Okay, well, I'll go first. You were measuring the vertebrae. From those measurements, can you get an idea of total size? It sounds like you at least determined that it was 2 separate Stegosauruses, is that correct?
Just
one.
Yes, but they
Okay.
had the 3 vertebrae. I was saying in this slide, that most likely it probably wouldn't have been. We don't have evidence. We have the pelvis and the vertebrae next to each other. I believe that there was more kind of like another pelvis that would or anywhere in the surrounding.
Sorry, I missed that part. Now we got a couple more questions over there.
Do you know how big that map was that like showed all the findings on it? How big of an area it actually was? Because when you say that we found pelvis near it, but your star was more up to the right, that kind of looked like 2 different areas, but you're saying it's the same. So how big of an area are we talking?
I don't know the exact size, but since, I kind of, the likelihood of my star is more of a hypothesis. I've never been to the quarry. I don't know exactly where it was done, but knowing that even that they were readily near each other, we can kind of just make the assumption.
It's about 3 feet.
Can you guess whether it was an adolescent or an adult? Animal from the bone?
I'm sure, somebody, better with more experience than me, I would assume, do it from the size and my own personal opinion, that was probably, adult.
Any other questions? Okay, let's thank the one more time. All right, I think we're just about ready to start our final session of our Geoscience Day. We have 4 more presentations for you. The next 3 are gonna deal with diatoms and climate, and then the last one, we're gonna give you something completely different with structural geology and finally some hard rocks discussion. Sorry, I'm a little biased. All the talks have been great so far today. I've really been enjoying all the presentations. But without further ado, our next presenter is 𝐤𝐺 He'll be speaking on using diatom size to reconstruct Holocene Southern Ocean climate. All yours, Josh.
All right, thank you guys for coming out. My name is Josh Mitchell, and today I will be talking about using diatoms to reconstruct Holocene Southern Ocean climate. All right, so I've been looking at the diatom frage curta, and it is found throughout Antarctica. I've been looking, this research was done off of the Mertz Glacier. So they drilled into the bottom of the seafloor through the mud and collected sediment cores with fossils of the diatom throughout. This data dates back to about 12,000 years ago, and multiple different data points were collected. So diatom size can show evidence of climate change. So here's the diatom. It thrives in sea ice, and it also thrives with lower temperatures. So the diatom size correlates directly to iron concentration. So basically, if there's a lot of iron, high iron content in the water, the diatom will increase in size. Vice versa, if there's lower iron concentrations, it'll be smaller in size. Okay, so diatoms contain silica-based cell walls. These are very important in obtaining nutrients. This is a very more complex way of describing the process, but again, they're very important. They also provide external defense against predators and can also defend the diatom against UV radiation. It's also important in collecting the nutrients. So these are diatoms, and whenever the diatom nutrient availability is high, the diatom sinks. So with more iron, they become denser. The frustules, which are the shells of the diatom, created to sink, and with lower iron content, it will rise to the surface. So this can be used to see, basically tell like the iron content at the specific time. So diatoms also are very important in the ecosystem for, they absorb carbon dioxide. They also then take that carbon dioxide, provide it to the ecosystem and oxygen. And diatoms are very important because, believe it or not, it's between about 20 to 40% of the oxygen we breathe are generated from diatoms. So yeah, this is just an image describing kind of the food web and how they provide oxygen. The oxygen then circulates throughout other oceans from the Southern Ocean, which shows why the Southern Ocean is very important. Okay, so this is a chart from a more modern chart, and you can see that these areas are losing mass and these are gaining mass. That mass would be sea ice. So right here is where our study is done. And throughout the course of the study, sea ice throughout the time dating back throughout the Holocene, this area has been gaining sea ice. So this is a diagram explaining, the basics of the ocean warms and temperatures are rising, which causes the ice to melt. With colder temperatures, there would be more sea ice in the water. All right, so here's some graphs that I created based on the data. And this first one is relative abundance. So you can see about 12,000 years ago, the data was all very clumped together between 10 and 30% mostly, until about 8,000, 7,000 years ago. It began to gradually ascend up to about nowadays, or let's say 1,000 years ago, it was around 60%. So the reason this relative abundance could show that there's a gain of sea ice at this time. Colder waters correlate to more sea ice. This graph is absolute abundance. So again, very variable back in 1,000 years ago, until you hit about the 8,300 mark, where you can see there's much lower fossils per gram of absolute abundance, which means that there's just a lot less diatoms in the water throughout this time. So here we have average length versus time, and as you can see, there's a common theme. Around 8,000, everything becomes very different, very big difference in data. This could be correlated to maybe like gaining sea ice, melting sea ice, gaining sea ice, and such throughout that time. So here we have the mean okay, so this is the difference between the maximum size and the mean size, which is another way of showing higher nutrient content with higher sizes. And so when we have a huge variability right here, that could mean some things. Basically at that point in time, there was probably a lot of melting sea ice in the region. Okay, so this graph is CT percentage. So CT is the bristles on the diatom, and basically, as you can see, that a lot smaller numbers here. This can just correlate that this was a lot more murky, cloudy waters, more pollutants to this time where there's a lot more clear water. Okay, so this graph shows the depth from the seafloor that was drilled into to collect the data. So right here would be 0 meters into the seafloor. Up here is 1,800 meters into the seafloor. So you can see back up until about 8,300 years ago, it was very consistent, more of a decline. Then it gradually evened out a little bit. This could be correlated to more shallower into the seafloor. The fossils were found throughout time. And again, we have this graphic just to show how all of those graphs relate to rising temperatures, melting sea ice. So to conclude, throughout analysis, I decided that yes, climate change can be shown during the Holocene. This graph shows some changed over time. Over the time, there's been obviously raising temperatures. And then further research could be done upon this idea. Basically, I mean, you have Antarctica, you can take a different species, a different time period, a different location in Antarctica, I mean, even anywhere else in the world, really, but you could take those quantities and do what you would like with them. And yeah, I don't have to thank you, Slab, but I would like to thank Dr. Warnock for assisting me in the research. And yeah, thank you very much.
It's time for a couple questions. We'll go first, or you want me to? I can tell you about, put your hand up. Josh, I'm sorry, I forget which one of your plots this was, but you started talking about, a spike going up, where it was just, I think it was a higher percentage of total amount of diatoms, and then it went straight back down, and you kind of highlighted that as melting sea ice. But wouldn't it be either the spike goes up, you get melting sea ice, or the spike goes down, you get melting sea ice? Because I would assume from what you were saying, it has to do with how many nutrients are in the water at the time. So what would you expect? What would create that spike of nutrients?
So I think I had kind of a stick, but basically that spike. Maybe it's more like an increase in nutrients in the water,
Creating the upward tick of the diatoms, the total abundance.
Yeah. More sea ice correlates to more diatoms. So I would assume that's. Yeah, I would assume that's correct.
You answered my question. So 𝐷 is a proxy for sea ice volume.
Mhm.
So more abundant, more diatoms means more sea ice. That's what I was trying to.
Yeah, that's true.
Any other questions? Pausing because we have a couple minutes until the next presentation. Katie, do we have any questions at all online?
We do not.
If anyone's listening online, it's okay to post questions and we will read them out loud.
Mind the members.
Oh, do you? Okay, great. All right. Well, if there are no more questions, then we'll thank Josh and stop making him stuff around.
Thanks, Josh.
All right, let's move on to our next presentation. Presenter who just happens to have a very sharp diatom tie on today. If you have not noticed, I'm jealous. That's why I'm breaking it out. Let's see. All right, I gotta get on this. If you'll excuse me, I'll just leave during your talk.
Okay.
All right.
Let me.
Our next presenter is Bailey Campbell, who will be speaking on effects of global temperatures on the abundance of marine diatoms.
Good morning, everybody. So the oceans act as vast climate engines for essentially everything. They store and redistribute heat. They can exchange gases with the atmosphere, and they are also carbon sequestration. And what is mostly important is the Antarctic polar front, right around Antarctica. That is where the cold waters of the Antarctic Ocean meet the warmer waters coming down from the north. And the shifts there, they can affect sea ice, it can also affect ocean currents. I apologize for my blurry ocean current map. I was supposed to fix it and forgot. I was trying to fix so many things. And they can also affect jet stream. Now, diatoms, while they're still living, are the base of many food webs. They're also found in almost every aquatic body of water, which sounds like a misnomer, but happens. And like I said, they are important for the exchange of carbon because they pull carbon down and into the deep oceans and it stores there. And now I focused mainly on two different types of diatoms.
the Antarctic diatoms, which are the cold water diatoms, and the non-Antarctic diatoms, which are warmer water diatoms. And they are good indicators for climate change because they are sensitive to changes in temperature and nutrients. And their shells, which are made of silica, preserved well in the sediment, so even when they are long dead, we can still study them. And we can also trace climate shifts using them. So here I have an example of 𝐉𝐻𝐻𝐿𝐼𝐻 Perchulis, which is a Antarctic diatom, so it's a cold water diatom. And Rural-Suburban, which is one of the warmer non-Antarctic diatoms. And there I have the current age model that I've been basing my data off of. And my data essentially came from sediment cores, which were taken from the ocean on the ship 𝐿𝐺 resolution. It has been drilled into me that it is a ship and not a boat. I don't wanna offend anybody else, the ship crew. So my samples came from 3 different sites, all drilled by the 𝐺𝐤. I got equatorial Pacific waters off of the western coast of South America. And 2 from the more southern oceans. I have 1 off of the tip of South America and in Iceberg Alley in Antarctica. So I have the equatorial Pacific, I have a mid-latitudes, which is the tip of South America, and I have my polar. Now, in order to get my samples, I had to grind up the sediment in very small amounts because it's very expensive to get here. I would then put it in a specimen jar with a peroxide mixture to kill anything that was still biological. So I didn't want to speed my data in any way. It would then get put into the beaker squared, which would be filled with water. There would be a slide and a cover slip on the stage in there. And then I would give it a minute to like settle some. And then I would turn on the valve, which is the tube there, to do 1 drip at a time, very slowly. Because if you try to go any faster than that, all of your hard work just goes right down the drain. And then I would give it like a couple days or so usually, so I could make sure it was all drained out. And then that is what my heated slide would look like. So now I'm gonna put it on the microscope with a very fancy camera attached. And hopefully be able to look at and identify some of my diatoms. Now, the Antarctic species, like Perchulis and Campia Antarctica, they are the ones that like it very cold. And they were mostly around in the last glacial maximum, which is right around here, which is when everything was very cold and they flourished in that time frame. The non-Antarctic diatom species love it when it's warm, like I said earlier. I have Pechulis nodulifera, I hope I said that correctly, and Perez alpata again. The one on the left was mostly found in the equatorial Pacific waters. Didn't find much of it in the other 2 samples. And Perez, that was mostly in the mid-latitude sample, so off of the tip of South America. And they were in marine isotope stage 5, which was an interglacial period when it was mostly warmer. So right up there at top is where they would have been in the climate model. Now, I do have a slight comparison here between my cold water diatoms and my warm water diatoms. So Perez alpata down there, that is its percentage of its abundance. So you can tell whenever it starts to spike, that is when it is warmer. And I have another picture there, in case you forgot what it looked like from the last slide. And over here, we have Perchulis, where it did have some spikes in the warmer section, but that's because that's where there was like a healthy mix between the populations, which would have been during the mid-latitude site. That is when it starts to majorly spike. That's when you can tell you're in the cold section again. So back into the last glacial maximum. And then the one on the bottom was all of my samples put together. So I did 21 slides and it was a lot.
And at one point, my samples did get up to 8 million fossils per gram, which. But I didn't have to identify that many. But that's, again, it was over time. So. Here I was comparing my chart that I was able to get with the known climate model. So MIS5, which is right here on this point here. It's kind of zoomed in here, but you can tell by the spikies as Dr. Warnock called them for me. If we were to zoom in on that one, we would be able to see the same spikes as well. The last glacial maximum, it was about here. Somewhat close. I was missing some data. And then the Holocene, which was at the very beginning. So we're looking at least about 120,000 years ago, my data spans. And this section here is whenever sea level was lower. So I lost time. It was the mud was being eroded away. And I wasn't able to get any good samples there for that. And then again, just reiterating that we want like a decent amount of diatoms that are still living because they are a big deal with the biological pump. So giving us oxygen, taking the carbon out of the atmosphere, just essentially being helpful little things all around for everybody. And then to wrap it up, they are sensitive to environmental changes, which is why we study them. They do preserve well due to their silica shells. So like I said earlier, you can study them for a very long time after they've been dead for a very long time. And if what I did see in my data and from past data is that if the current climate trends keep going towards warming, we will see a dip in the Antarctic diatoms and a rise in the non-Antarctic diatoms. Which is a bad and a good thing, because if the Antarctic diatoms go, then the climate and all of it is definitely getting warmer and it could increase climate change, which is not a good thing. And I don't have a thank you slide, but I would like to thank Dr. Warnock for helping me a lot. Dr. Farnsworth for essentially holding my hand through the PowerPoint creation process. And even though he left, Dr. Hoban, because one of my samples actually came from the drill site, the drill he was on. The site he worked.
We do have time for questions if anybody has any.
Okay, so if you take a diatom from long ago and a diatom from today, have they evolved? Do they look identical or do they look quite different?
They look different.
They do. Okay, so if you didn't know and we presented you with one from, I don't know, millions of years ago and one from today, you would know right away, oh, this one is today and this one's the old one. I mean, there's probably incredible variety among the diatoms, but I just wonder if they evolved.
I don't think I would be able to tell. It would take someone with much more training and a better eye than I to be able to tell that difference. What's the question?
Which one's your favorite?
I like the camping in Antarctica mostly because it looks like a pair of pants or like SpongeBob shorts. It's also one of the easiest for me to be able to identify because it doesn't do the
So do you think diatom records from the equatorial region or from near Antarctica, are either one of those a better location to be doing this kind of work? Or are they sort of just talking about different parts of the world?
I'd say maybe Antarctica because it seems like there's being a lot of research being done there. And there seems to be quite a variety. I'm not 100% positive. I just wanted to have different geographic areas so I can have a good collection of data.
So I know you said it on your mock-up, but I missed it. Where'd you get your time?
Etsy, it was like $40.
Awesome, thank you.
I did college, well, it's like this one fast.
Everyone should be experts on diatoms after today.
So I may have missed it, just each dot on the plot, each dot is, as you mentioned, something like 10⁶, like numbers, the big numbers. So it's just what each dot is like a count, just a little fleshed out so I can understand. Yeah, each of those spots, like, yeah.
Each spot would be a peak where they were mostly abundant, and then they would either start to drop off.
But you counted, how did you get a number? I mean, you didn't count it like 10⁶, but you estimated it from. Right, so I'm just curious how that worked.
I essentially went through and I counted what I could, and also I did 33 fields of view.
Okay.
And that seems like an interesting number, just because the first time when I started doing it, I ran out of time, so I had to go to a class, so I stopped at 33.
Oh.
So I just made everyone after that 33 to be consistent. And I just counted however many at a time, and we're not gonna do like an equation in Excel to
Okay,
figure that.
to scale it up to
Yeah.
per gram. Okay.
Yeah.
Okay.
Any other questions? Okay, let's thank Bailey once more.
If we've learned anything today, it's the value of diatoms in earth science research. Understanding water quality, climate change over time, past and present. And clearly how many students want to work with Dr. Warnock. That's 90% of our presentations today. And I thanked him personally, quietly over here, but I'll just embarrass him now. This guy did so many talks in the last year. I don't know how he slept.
I didn't.
So thank you to Dr. Warnock for all he's done to help guide these research projects, because this is not a small lift. Yeah.
So just a comment that there's a peanut gallery comment from YouTube that says these presentations are slayed.
You that way with that?
There are no emojis to.
All right, well,
Yes.
yes, maybe.
You never know.
All right, excellent. Well, let's move up to our next presenter. Hannah Taylor will be speaking on using diatom microfossils to understand paleo nutrient availability in the Scotia Sea.
Hi, everybody. Thank you for coming. And let's just jump into it. So the Scotia Sea is important for paleoclimate research due to its location. So as we can see here, it is located right between Antarctica and South America. So here is the Scotia Sea, otherwise, and here is the Drake Passage. It is important because the Antarctic Circumpolar Current, or the AAC, located on this bathymetry map, shows that warmer water coming from the equator the warmer water is coming down from the equator, following the AAC, introducing more warm water into that area, which also aids in ice melting and breaking off of the Antarctic continent. So my location was the Prairie Basin, which is 1538, right there by that arrow. And with that, we can see here, this is an area where this ice would break off and melt in that water, so leaving a lot of interesting things. So I have two diatoms that I followed, the first being the 𝐿𝐵𝐻 𝐼𝐺𝐻. Both diatoms are a siliceous algae microfossil leaving behind a clear skeleton. So for the 𝐿𝐵𝐻 it is a pennate diatom, and it is more abundant than the next one, and it can survive in colder water, and that water has to be a more nutrient dense water. So my next diatom is the 𝐿𝐵𝐻, and this diatom is bigger than the other one, and it can survive in much warmer water. It only survives in much warmer water, and it doesn't need to be as nutrient dense as the 𝐿𝐵𝐻 has to have. So this information was gathered by the JOIDES resolution in 2019. This was funded by the IODP, or the International Ocean Discovery Program. So this ship right here is the JOIDES resolution. It is a drilling ship. And with this ship, it is sadly retired now, but in 2019, it would go along that path and drill down to the ocean floor, collecting core samples, which are seen in that image on the very left for everyone else. So in that sample, we get our diatom fossils as well, microfossils, as well as Earth's paleomagnetic record, which can be compared to the known data and give us an accurate timescale. So I processed this sediment is in the lab, sorry. I used very little of that sample. As you can see, it is freeze-dried. They pretty much just stick that in and freeze-dry it. Everything's great. So we take a little bit of that sample, I ground it with a mortar and pestle, and my goal was to get between 0.03 and 0.06 grams, mainly because it's expensive and a lot of time and a lot of work to get all of that sediment from the ocean floor to a lab. So then after weighing that sample, I put it in a specimen jar and added a hydrogen peroxide solution to help kill off any biotic material left. That way it doesn't skew my data. And this hydrogen peroxide solution will not harm the diatom skeletons in any way, shape, or form. I pretty much just let this sit overnight. That way I was ensured that everything was gone and I could prepare multiple samples at the same time, up to 4. All right, so with that prepared sample, I then added it to this beaker squared, which is a settling chamber. I followed the 𝐼𝐺𝐻 method for this, where you could pretty much make multiple slides off of this one sample, which is a great thing. So with that, I would fill the water up to this line here, add in a glass slide and a glass cover slip. And once I added that water in, my goal was to make sure everything was still. So I would add in the specimen with a little bit of a dish soap solution to help with the dissolution process. I let everything settle for a couple of hours just to make sure that I didn't have anything free floating because I didn't want to mess up my data. So after everything has had a chance to sit and settle down, I would then turn on this little blue valve, as you can see here, as a drop. So that way it wouldn't create a current, unsettling the water and taking all of my sample and all that work down the drain. So this could take anywhere from a couple of hours to a couple of days, depending on this little tube here. Sometimes it would just stop running, so you'd have to wait even longer. So with this, after the water passes the stage, you're left with your slide and your cover slip. And with that, you would just take that little glass cover. You would just take the little glass cover slip off, get rid of that glass slide because that is not what we're looking for. So with that, we then take a clean glass slide, add a little bit of glue, and gently set that cover slip sample side down to help avoid creating any air bubbles because we want to protect the sample on there so it can be used over and over again since it is expensive. So after you would set that sample down, you let it dry with an optic glue. So we use a UV light, as Austin and Alexa both have used. And then you're done. You just put your label on with the expedition number, your site, how deep it was, and then how much you used was what I put on. All right, and then with those slides, we would then put it into the Olympuscope here. We are fortunate enough at IUP to have one with 2 monitors. So with that first monitor, it was a blown up version of what we would see on the Olympuscope, and it helped you better see what was underneath each diatom, because a lot of the times they stacked up on top of each other. So you could just turn your focus and see things underneath and see things over top. And it also aided with the identification process. And then the next monitor, it was a free monitor. You could use whatever software you felt most comfortable with for logging your data. I chose Excel because everyone uses it. And I just added this in. It was a cute little fun thing for me. I liked it a lot. It's a counter, so you wouldn't get lost with how many views you've done. You could also use it to count how many diatoms you've seen as well for up to 5 different species, which I did. All right. So how I collected the diatoms for each slide I used 20 different views, mainly because that's similar to Bailey. It's how long it took me to get through that first slide. Because there's a lot, especially for the more abundant Flagellariopsis curculensis. I think for my first sample, I had between 40 to 50 of them. So since the Flagellariopsis curculensis is a pinnate diatom, for getting its volume, I multiplied it by the width and the length and then by a factor of 0.8. That way, it gave me a more accurate representation of its volume on the inside. It is the most recognized way to get its volume. And on the very bottom there, you can see one of the broken ones. That was one that was excluded, mainly because it was harder to see its length, because as it doesn't line up very well with some of them. All right, and then for my next diatom, for the Thalassiosaura lentigienosa, I butchered that, that's okay. I took a radial measurement and used the sphere equation to get my actual volume for that one. And with that one, I took a radial measurement rather than a circumference due to the fact that a lot of them were broken. So I could easily depict where the edge of this was going to be and where the center would be. And that way it wouldn't skew and mess up my data, and I wouldn't have a hard time doing that. All right, so for the Flagellariopsis curculensis, we're going to start here. This is the age in thousands of years by the average volume. So as we can see here, that there are smaller diatoms, there are smaller Flagellariopsis curculensis around 9.5 thousand years ago, which would indicate that there was not a lot of nutrients in the water. So as we see that we build up closer to the 6, it indicates that there's more nutrients available, which may be warming, but we don't know as of right now, but we will in a second. We see a stiff drop, which indicates that they used up whatever nutrients relatively very quickly. And then we get a slight build, and then we're into our present. All right, and then for the Thalassiosaura lentigienosa, we're going to start here 10,000 years ago again. It's the same layout as the other one, but as we can see here, that this graph shares a point with the other one, and about 6,000 years ago, there's a high point, which here indicates that the temperature rose relatively quickly, which it may be so sharp due to the fact that I didn't have all of that data for that site, mainly because I only did about 20-ish views. So if I would have done more, maybe I would have gotten a different result. But here, this is what I have. As you can see, since the Thalassiosaura lentigienosa grows better in warmer environments, it doesn't have to be a nutrient dense. So as our next slide shows, a comparison between these two and the diatom abundance chart. So as we can see closer here, we can verify that around 6,000 years ago, we see the same spike as well as the increase here. So looking at the diatom abundance chart, which was provided to me by Dr. Warnow, we see here that around the 6,000 years ago arc, that there is an increase in both abundance and for both of these species, which would indicate that there was a warmer period allowing for more nutrients to be available during that time. As well as looking at the lower peaks here, which show the drastic drop. So that maybe for the Thalassiosaura lentigienosa, that there was this better drop here for the temperature, so indicating possibly a cooler period. And then for the curculensis, we see here around 8,000 years ago, which would be following there, but there is another drop there, which would indicate that the nutrients level had decreased. Alrighty, and I want to say thank you to Dr. Warnock for helping me through all of this, as well as Dr. Katie Farnsworth for helping me even be able to be up here today, or else I'd be probably freaking out in the corner.
We have any questions?
Yeah.
Around 4,000 years ago, it looks like on the diatom abundance plot, which seems like there are more times sampled. You've got sort of a smooth connected, like just.
Yeah.
So the hope would be if you could get more samples in the age dimension through time, you'd see some of that complexity. Is that right?
That would be, yes. Mainly because I only used about 10 slides compared to where they went through all the samples at all the levels. They got even better results than what I would have had. So this would be a great thing for someone else to follow up into the future, possibly building off of this and even doing their own project on it.
Finer resolution.
Yeah. So hopefully opening the door for someone to take this over.
I have a methods question.
Yeah.
I think you said this and I just kind of miss it, but yeah, actually go, you skip past one,
Oh.
go, yeah, right there. I think you were talking about taking the measurements.
Yeah.
Obviously on the left, we got length versus the total kind of width there, and then you went down to the bottom right. Did you measure fragments as well as the full specimens?
Yes.
And what sort of potential error do you see if you're measuring the fragments? Yeah, I guess can you walk us through that just a little bit of like, you know, what potential problems are there, or how did you alleviate those problems?
So the potential problem would be that I would not correctly estimate where the actual side of the diatom would be. So the best goal would be to always go smaller rather than go larger, because it can base off of what we already found. So looking at the ones that I've already measured, I can see where they would branch off. So if I could overlap a couple images, it would help. But typically, I try to follow where it would mean, because a lot of them, as you can see, like there's the stacking over here, but you get a closer peek over here. So a lot of them, this one isn't my image. This is one from Dr. Warnock, because I didn't think about getting a photo of one of those until the very last second. So a lot of them, if I couldn't identify on my own where it would be, I left them out, because a lot of times, a lot of them could be just fragmented, and you could have multiple of the same one in the same slide.
Thank you very much. I appreciate it.
Follow up, is the K as the F 𝐿𝐴 length is it cylindrical?
So it is a pennate diatom, meaning that it has a larger middle than what the other ones have, and it would look more like a piece of orzo, right? Yeah, so kind of cylindrical, but skinnier.
But is it, so if you could slice on the short dimension, would it be a perfect circle? Or is it flattened? That's good. I didn't know, because you're estimating volumes, right?
I would say it's kind of more flat,
Okay.
more like following that shape.
It's like the orzo, okay.
Yeah.
Any other questions for Hannah? Okay, seeing none, let's thank her one more time. Right, the last thing that I learned about diatoms here today is the faster you say the names, the more you sound like you know you're pronouncing it correctly. Is that right, Dr. Warnock?
Helps.
It does. Just go fast, just go through it real fast, don't hesitate.
If you have a stutter, it makes it worse.
Okay, all right, this brings us to our last student presentation of the day. There's still more to come. Last student presentation, last but not least, we have Marisol Flores, who will be speaking on mapping mineral chemistry in exhumed seafloor rocks, Central Range, Taiwan.
Good morning, everyone. Real quickly, I just want to thank everyone for coming out here today. Congratulations to my fellow presenters. We did it. It's over. Well,
It's almost over.
But yeah, so like Nick said, today I'll be talking about mineral chemistry in Taiwan. So Taiwan is located on the edge of the Philippine Sea Plate. And it's a very active area. So I'm going to point out a few things. We'll be moving around a lot. But Taiwan itself wasn't always there, right? So how did it get started? The Luzon Arc right here is a volcanic range that extends from Taiwan itself currently to the Philippines. Now, originally, the Luzon Arc was actually subducting with the South China Sea. This subduction zone moved towards the continental Eurasian plate. And because of that, it basically stopped subducting because the continental plate didn't want to subduct. So we get a collision. This collision results in a lot of uplift and exhumation processes. Exhumation is the processes as to why or how rocks got to the surface. So we're going to be exploring some of that evidence, some strain deformation areas, and the topographic changes of Taiwan itself. I included a visual of this subduction zone. The actual samples we're going to be focusing on are from the Yuli Belt, which is in the central range of Taiwan, which is in this area right here. And it's estimated, if you really want to think about it this way, Taiwan is moving closer to China every year. And this is around like 82 millimeters per year. Okay, so when we think of how Taiwan came to be, two plates colliding, this model isn't entirely accurate. It's not wrong, but there's different processes that come along with it.
For example, we see, Tim Burn actually theorizes that there's a change of subduction zones direction. So, in the northern part of the island, the subduction plate, the Philippine Sea Plate actually dives under the Eurasian Plate, and in the southern part of the island, the opposite is true. Where our samples come from, the Central Range, there's evidence that actually shows this change. So it's very interesting to think about. I included a 2D model, which isn't wrong. This isn't wrong, but I just want to include that our evidence actually shows that the evidence of exhumation in Taiwan is more 3D. So what you see here is exhumation in the Central Range. In our reality, it'll actually be 3D, so it'll be like coming towards you. I also included an image, a visual of just kind of the direction changing of the subduction zones. So as subduction zones change, we see something called underplating. Underplating results in uplift and exhumation. So this is, you can think of like the foot wall, something being subducted, and the hanging wall. And then when we see this change and shift in deformation, we also see some uplift, which is where we get that high areas of topographic changes in Taiwan. Okay, so we know that this is true, that we see uplift and everything because of the evidence we see geographically and also geology-wise, right? So like I mentioned, we do see a shear zone, we see uplifted materials, which we can indicate, or which we can say are evidence of a shear zone. There's an extensional shear zone in the Central Range of Taiwan. And we know that this is true because we see things like this. These are porphyroblasts, or you'll see them called pebbly phyllites later in my slides. Porphyroblasts form as rocks get deformed. So anytime we see these anywhere, it's evidence of a shear zone. And a shear zone is just a weak zone that allows things to shift and slide easily. Okay, so why do we care about Taiwan? Other than the fact that like I mentioned, it's a very active area. It is one of the few active areas that are currently active. And it allows us to explore very rare and well-preserved outcrops, samples, and its geology in general is just very, very interesting. So our samples come from a very well-preserved outcrop in the Central Range that we theorize is seafloor, metamorphic basalt, aka greenstone. This is an image of the outcrop of where our samples came from. You can see the greenstone is the lighter areas, and the darker parts are phyllite actually. And this environment is indicative of just marine mud and volcanic ash deposits. And yeah, I just really want to emphasize it's a very active area, and it's very well preserved. Okay. So even just looking at the thin sections, I'm going to focus specifically on the northeast and mostly on the northeast view and the northwest, just because this one has the phyllite. This thin section actually has the phyllite, so we can kind of see a relationship between the phyllite and the greenstone itself. So even just looking at the thin sections, we see the porphyroblasts, which are again indicative of the high strain. This thin section, the northeast view, is actually looking at the CY or CX plane. It would be the longer view, and then this one would be looking towards the CY plane. So these two thin sections are 90 degrees to each other. This is very helpful in determining strain directions and things like that. And previous Team Tecto members, Lauren and Bennett, were able to do more work on that. But even just looking at these things, again, you can see the strain. I also would like to point out that the pebbly phyllites, or the porphyroblasts closer to the phyllite, are more intact. You can kind of see that here, while in the greenstone they are more deformed. And we're going to get into a bit as to why later. All right, so even just looking at the thin section again, this is the northeast view. We see the evidence of the shear strain and the type of shearing. So if you look to the right here, this is the darker spot is the phyllite. This area over here is the greenstone. You can see that the phyllite has cannulations, which are very, very interesting.
And I'll bring those back up again later. But the crenellations show us that the phyllite is kind of moving northward, whereas to the direction of the greenstone, it's moving southward. So we see it's evidence of simple shearing. John always likes to use the card deck example, but if you look at it this way, it's quite literally two things shifting, showing evidence of simple shearing. Now, what we had was a bunch of thin sections and a bunch of data that we didn't know what to do with. So what John did during COVID, he sent his actual thin sections to Washington State University, where they were able to do something called electron microprobe analysis on them. They gave us that 𝐕𝐴 data. 𝐕𝐴 data looks like coding. It goes over my head personally, but I was able to take that data, upload it into something called 𝐸Maps_Tools. 𝐸Maps_Tools is like a geochemical website where it will help you create a map of your own thin section. They also gave us the high resolution images of spot analyses they specifically did, and the EDS spectrums, which is the energy dispersive X-ray spectroscopy of the actual spot analyses they did to give us the geochemical data. This is actually an image I took from looking at the thin section under the scope. Now, originally what I did was try to find the actual spot that they mapped up in the thin section itself. And if you've ever looked at a scope for over 5 minutes, your eyes hurt. So I wanted to do a little bit more than just looking at it with my own eyes. I tried to bring back some mineralogy knowledge, which is a little bit lost, might need to retake the class. But I was able to kind of analyze that and look at the EDS spectrums, which I'll get into a little bit further in the next slide. But I just want to point out, even just looking at the thin section again, you can see evidence. This is the phyllite. You can see evidence of deformation and a porphoblast potentially forming upward. Okay, so what I was able to do was, again, take this 𝐕𝐴 data and create a thin section on 𝐸Maps_Tools. So I went onto 𝐸Maps_Tools, uploaded the data, and this is the thin section that it gave me. Now, 𝐸Maps_Tools allows you to basically pick an element, and it'll tell you the frequency on a color range of that element. So I picked aluminum specifically, aluminum oxide weight percentage, because it showed us the highest, from what I noted, the highest color range. So I really wanted to point out the differences. This one specifically is the northeast one spot. So it's like all the way in the corner, if I could reach it, but it's closer to the phyllite, which is important. And you can see the porphoblast here and a tail forming. And upon further investigation in terms of the EDS spectrums, I really had to do a lot of reading on this. And I was able to narrow down what minerals were present in these areas using mineralogy textbooks, a data set, or a geochemical data website called 𝐼𝐷𝐻. I bothered Nick a few times, and we saw the same minerals throughout the thin sections. However, some of them, in this case, the andesite over here, was a bit more iron-rich and calcium-rich, so on and so forth. Now, again, this one's by the phyllite. Now, this one is in the greenstone. It's all the spot all the way to the left over here. I guess my left. We saw that the one that was closer to the greenstone was a lot more deformed and had higher aluminum content. Yeah, I also just want to point out that the greenstone itself is well, I'll get back to it. Let me switch to the next slide. Yeah, so one thing I noted within the greenstone itself was that the minerals in the greenstone showed higher peaks of iron in their EDS spectrums. So a lot of the minerals I saw showed like peak of iron at the end over here, but a lot of the ones in the greenstone, which I included examples of right here, showed just a small peak of iron at the end. These were from the XY plane, which again doesn't show the relationship between the phyllite, it's the whole greenstone itself. But I thought it was interesting because upon understanding or trying to understand what this means, I read somewhere that the iron itself, peaks at the end, can be indicative of metamorphic transitions. So this could mean that the greenstone was potentially undergoing higher pressure, higher temperatures, so on and so forth. So, to wrap it up, our analysis of the greenstone of the phyllite shows or reveals that there's a strain gradient between the two. So the phyllite, think about this, the top and the bottom as your phyllite, and the middle as your greenstone. As we get closer towards the middle of the greenstone, things become more deformed. Now, we don't really know why this is, which is why we would like to investigate this further. The greenstone, again, I point us back to the granulations. So when we think of greenstone, or sorry, the phyllite, we think of it being flaky, potentially even fragile. So this theory is kind of counterintuitive. We think that the phyllite would be easily deformed. But I point back to the granulations. Maybe the granulations act as some sort of shield, which are worth further investigation as well. So currently, I'm working on creating a mineral key for future members. Today, we only saw 11 out of the 60-some minerals I had to identify. So once I, create that key, I'm hoping to pass that down so somebody can actually classify everything onto XMAP tools. It would be interesting to see how mineral shapes, because each mineral has their own shape, crystal habit, et cetera, et cetera. It'll be interesting how they differentiate between closer to phyllite or away from the phyllite, and what that means about what's occurring and in the not only in the subduction and collision area, but as a whole at the exhumation processes. So I just want to say a huge thank you to Professor Lewis here for really helping me make this project come to light. And shout out to previous Team Tecto members. I used a lot of their theories and hypotheses, so it really, really helped. And shout out to my mom who's watching and my baby sister. But thank you so much. I'll take any questions.
Any questions from Marisol?
Could there be some, I'm inviting you to speculate if, since you have this unexpected mechanical result, we all think phyllite is, that's unique, that's where decomas happen. But because you're exhuming rapidly and there's strain, and there's metamorphism going on, could it be that minerals are expelling water or some other component that could affect them mechanically? Is that possible?
Yeah, definitely worth more investigation. We don't really know where our sample came from, right? So we theorize it's seafloor, old seafloor, but it could be old seafloor from China or from, wherever else. So it could be that maybe it got mixed up somewhere else. And that's why we see what we see in terms of the strain.
A general question. You mentioned that this area is active and that's what sort of drove the research in the area. Can you describe what sort of activity are you referring to and, maybe the level of importance of this particular project?
Yeah, okay. So, there's a lot of theories as to how Taiwan came to be, right? When we think of the level of activity, a lot of people think that the collision between the two plates, actually created like some sort of gradient in like the age of the rocks and the age of the topography. So for example, the northern part of the island would be showing signs of like older topography. And then the central part of the island where we're at is like the current active area. And then the southern part of the island has yet to exhume and show signs of exhumation. However, when we actually look at the samples, we see that all of them came to be at the same time. Maybe not all, but they're all around the same time period. So it just points to maybe, I was just talking to John, this is all like within the last 1,000,000 years, which is geologically very quickly and very recent. So again, there's just more research to be done in terms of what this means. But the fact that it's there points to its importance.
Thank you very much. I think we are out of time now. So let's finish. Anyway, that brings us to our alumni presentation of the day. Today we have Brock Kennedy be speaking. He was in class of 2018. He worked with Dr. Hoban on legacy gas wells. And usually when we often when we introduce our alumni speaker, we kind of go through their career path, but he's actually going to do that for us today. So I'm going to keep this real short and just welcome Brock and say it's all yours. Take over.
Hi guys, as Dr. Deardorff said, I'm Brock Kennedy, graduated in 2018 from back in the day when it was just the geoscience department. I've done a lot of changes and, excited to be here, really am. So, Dr. Thornburg called me a couple weeks ago and asked me to come back in, talk to you guys a little bit about my career arc since graduating in 2018. And then give you guys a little insight on some of the projects that I am actively working on the geotechnical side of things. That's myself and my research partner, Aaron Johnson. We did a talk, I mean, just like you guys did today, about legacy gas wells in Indiana County. So why did I choose IUP back in the day? Honestly, I wasn't the most prepared when choosing my university. When I was in high school, it was about this time. I was about ready to graduate high school. I had 3 hip surgeries before graduating high school. Went in for a doctor's checkup, rolled in my wheelchair, and the doctor said, "What are you gonna do when you graduate high school here in a couple months?" Says, "I don't know, man. I'm gonna go work in the drilling rig. I'm gonna be a brake hand." And the doctor kind of laughed. He's like, "Son, you're actually in a wheelchair right now. If you don't go to college or do something, you're gonna be in a wheelchair for a long time." So I was like, well, crap, I better figure something out. My grandpa found an ad for IUP geology in the newspaper, and I didn't do it the right way, but I applied. I didn't even know what I was signing up for, but I showed up one day. Dr. Hogan introduced himself. I told him, "What do you want to get out of this?" I said, "Dr. Hogan, I really don't know. It's nice to meet you, but I just want to do my 4 years and get out of here." And man, was I wrong there. The department had a huge impact on me. The professors that you have here are incredible. I'm so lucky that I fell into coming here in my weird way. They made a huge impact on me. They're way nicer than they need to be. They care about you. And it's a great program they have here. Yeah, I kind of came into this not knowing anything about geology. I live about an hour away from here. I was kind of a redneck here kid, kind of didn't have much exposure to many things. Again, my dream was to be a brake hand on a drilling crew. But the professors and the classes here really opened my mind. I remember sitting in Warnock's 204, historical geology, just walking in, would get my mind blown, thinking in hundreds of millions of years every day. Kind of a Carl Sagan quote that I really like. These professors showed me more than just a body of knowledge within science. They showed me a way of thinking. They opened my mind, and I'm very thankful for that. Dr. Lewis in 201 beating the crap out of me in the foundations. Almost made me quit. It's the first time I was actually academically challenged, but that was what I needed. To listen to the other students get berated by Deardorff's mineralogy class to learn all of those. That's what we needed.
Hear that? What you needed.
This was on our field course off the Warnock took us out to the Cleveland-Lloyd Dinosaur Quarry. I see some of you guys are still doing stuff out there. That's awesome. That trip, this is our most of our graduating class of 2018. Not all of them were seniors, but it fundamentally changed my life. First time out west, I still blab on about spending 3 weeks digging up dinosaur bones. It was incredible. And then the undergraduate research project was a good launching point. The first time I actually had to really try and present, and I think Dr. Hoven was out somewhere, and I kept breaking all the stuff in his lab and having to call him. It was a really good experience.
I remember
that. Again, coming to IUP, you get your primary skills and knowledge. Your geology majors, you came here for geology, understanding how to read topos, how to identify rocks. Those are all the things you knew you were signing up for. There's also a secondary set of skills. So those are all the things that you pick up along the way through your labs and classes. My first job while I was a senior at IUP, that was anything geology related, so I got an environmental or a land surveying job as an environmental tech from a company called Environmental Land Surveying Solutions here in Indiana. How I landed that job was Dr. Farnsworth took us out in one of our labs. We had to do simple field surveying. So when I was in the interview, I got some land surveying experience, and they ended up landing my first job, with those secondary skills I picked up along the way. So upon graduating here, I got hired by a company called Scientific Drilling International. They were a directional drilling company. Honestly, I had really no idea what I was signing up for, but I was just graduating and needed a job. So a little introduction to explain this job is, you gotta have kind of an understanding of how directional drilling works. Goes to the diagram on the top right. You can see a drill rig with a bunch of wells going down, fingering out in other ways. If you look at the rocks kind of illustrated there, as you guys know, law of superposition, rocks are kind of like pancakes. So back in the day when they were first destroying, getting oil and gas, drilling for oil and gas, they used to just drill vertical wells down into their rock unit, and they would suck it out like a straw. Now what they do is it's more economical to buy one piece of land, they drill a bunch of them down together, and then by the time they're in their pay unit, which is represented by that black unit, they're horizontal, fingering out all different ways to get more surface area, get more ROI on their wells. So when they started doing that, you have to introduce directional drilling. One of the problems with having a bunch of wells going down vertically together and fingering out is the Marcellus and PA is about 7,000 feet down, so you can't see with your eyes what's going on down there. So to get around that, they build a tool into their drill string called an MWD tool. It stands for measuring while drilling. Essentially, it's a fancy compass. It is their eyes. It gives them the inclination, the angle that they're at, their compass direction, and they can know their depth as well. And that's how they steer these things to know that they're going to hit their pay unit. One of the problems with using this fancy compass is if you see the well pads are kind of chaotic. A lot of times you get into a spot where you're right up against another cased well that's made of metal. When doesn't a compass work? Right next to the metal. So in some of their most critical positions, they go blind. We have to run a different type of tool down in the bottom left. That is a gyro tool that runs like a gyro, so it reads the rotation of the earth rather than relying on magnetics. We'd run it off of, in the bottom right corner is a wireline truck, basically a garbage truck with a big spool of wire. We'd run it down. We'd go down and we'd take a shot. You know, they're blind. We'd go down, take a shot, talk to the directional driller, say, hey, you're at this depth, this angle, facing this compass direction. They would steer and orient the rig. They would drill blind, go back in, take another survey shot. This job was really interesting. I didn't really know what I was signing up for, but drill rigs aren't cheap to run, and we come in when they went blind. So it cost about $20,000 an hour to run a drill rig, and sometimes they wouldn't always know when they went blind. So we were on call 24/7, 365. So it was quite the experience. I think I graduated here on a Saturday. Like the next Monday, I flew down to the Permian Basin and was working in West Texas. One time I got a phone call from a number I didn't know. I was at a concert in Pittsburgh. And they're like, is this Brock? I'm like, yeah. They're like, you got a 6 a.m. flight to Lafayette, Louisiana. I'm like, right. I went to the airport, slept in my truck, and woke up, shook the dust off, and spent the next month having a real bad time. But other geologists related job that I see with us in this field is exploration geologists, well planners. Somebody's got to read the rocks and plan these wells to maximize the ROI to extract whatever resource you want. There's things called a mud logger. There's geologists on site as the drilling spoils come back up. They're sitting there logging every, at 1,000 feet we see this kind of rock. At 1,500 feet we see this kind of rock. I ran the gyro tool and the MWD tools, but this is a wireline truck, and there's all kinds of different tests and geologic instruments that you can run on wireline as well. There's a whole bunch of careers out there that I never knew existed until I've seen them with my own eyes. If oil and gas isn't your thing, they use a lot of these directional drilling tools in other industries, like boring underneath rivers and railroads and highways for utilities and stuff like that. If oil and gas ain't your thing, or if you don't want to spend 6 months in West Texas, because I don't recommend that. But it was a very interesting job and I learned a lot, met a lot of good people. After about 2 years of this, I realized, hey, this on-call thing, 24/7 ain't really the life for me, but we only worked about 50% of the year. So I really wanted to get back into something geological, so I went to Texas, or I got accepted to Texas A&M, petroleum geology online master's program. Unfortunately, the next day, after I got accepted, my mother was killed in a car accident. So that was pretty unfortunate. So that kind of changed my priorities for a time, and I kind of shelved grad school for a while. I actually accepted a job with a company called TerraSound. What they did was got a position as a echolocator or echo sounder. We were going to map the seafloor. This was a couple months after the unfortunate situation that happened in my life. I realized that if I took this offshore surveying job, that it wasn't getting me to my goal of being home more and having a little bit more control in my life. So what I ended up doing is, about a week before I was supposed to leave for underwater training school, I called TerraSound and said, hey, I took another job. I actually ended up getting out of anything geology related for a couple of years. Took a job as a construction estimator for an electrical contractor. We'd build utility lines and stuff like that. So my job was actually to sit there and look at all the electrical prints, assign man hours and cost to it, and put in bids. Wasn't using my geology degree there, but I relied heavily on those secondary skills I was talking about. Things like mapping, organized notes, mathematics, and just general Excel, stuff like that. Believe me, that gets you a long way in the work industry. There's a big age gap between people our age. Well, I guess I'm a little older than you guys, but in their 20s, in the workforce, when I've seen everyone else is in their 50s. I don't know where all the 40-year-olds went, but a lot of these people don't really know how to use basic computer skills. One of the biggest things, the helpful things that I took from this department when I was doing this kind of work was quick and dirty maps. Dr. Farnsworth had a lab where we had to map water runoff in the local area, and we had to figure out a way to present it. We just made quick and dirty Google Earth maps, and that skill alone got me a long way. That's why I put that picture up on the right. That's one of my quick and dirty maps that I threw together. So anyways, I did estimating for like a year and a half. Was like, this ain't for me. I'm not really passionate about this. I want to get back into geology. So I called up 𝐚𝐿 and I was like, hey, I'm going to go to Pitt for grad school. In order to do that, I need to make more money, so I'm going back to the oil field. They said, okay. They actually kept me on part-time as a consultant, so I was doing both for about 6 to 8 months. Saved up enough money to go back to Pitt to grad school. Long story short, Pitt didn't let me in. In hindsight, I wish I was a better student. But nonetheless, I got accepted to Montana State for an environmental management program. When I found out that I didn't get into Pitt, I called the fine folks at 𝐻𝐿sback. I said, hey, Pitt didn't let me in. I know you guys are trying to help support me, but I think I'm just going to do this online environmental master's program. He said, the boss there called me. He's like, hold on, I'll call you back. Called me back about 20 minutes later, said, do you want the knowledge or do you want the management experience? I said, I guess either one. So why don't you come work for your management experience rather than go back to school? I said, that doesn't sound like a bad idea. So I ended up becoming a project manager there. Project manager is kind of the middleman between what's going on in the field on an active project, the owner, whoever's paying for the project, and the internal executives. You're kind of managing the budgets, making sure that the scope of the project doesn't change, dealing with field issues, customer issues, vendor relations, all those kind of things. Secondary skills that I learned there were how to be a professional, how to work in a team, communication skills, public speaking. What you guys went through today, that was probably the first time I ever actually had to publicly speak and be super nervous. That helps me when I'm sitting in a room full of executives explaining to them why we're going to lose $500,000. So all those things, all these skills that you've acquired, whether they're geology based or the secondary skills that I'm talking about, they're all helpful things. Some other geology related jobs I noticed in this kind of electrical construction realm We're environmental, inspectors, designers. There's a lot of stuff with access roads where you get into stuff with water delineation, wetland protection programs. There's soil scientists involved and a lot of shallow geophysical stuff. I don't know if you guys still have the GPR and shallow seismic and all that. A lot of times you do a lot of that kind of stuff to locate underground utilities so you don't hit them. It's kind of counterproductive when you're trying to build new power lines and you're wrecking the old ones in the ground. So from there, I started with this company called the Gregory Geotechnical Solutions or Services. That's where I'm at now. I'm a geotechnical project manager. I manage projects from cradle to grave. So it's, do the estimating, we get the project, see the duration of the project, and finally get paid for the project. We do a bunch of different projects, but interpretations of the local soil conditions in geologic, the underlying geology are keys for success and safety as well. I didn't really know much about geotechnical work until I started getting into it. Geotechnical stuff is the blend of, it's where heavy civil construction meets the underlying geology. So whether you realize it or not, there's geotechnical work all around you. This brand new beautiful building that they built sits on some type of deep foundation. They had to have a good understanding of the underlying geology to build it, to make sure it doesn't sink. Any bridge building, roads, deep foundations, pile driving, micro piles, retaining walls, slope stabilization, shoring. This is all geotechnical stuff. Every construction project, anything that's ever been built, takes a team of geologists, engineers, project managers, estimators, superintendents, laborers, support staff. Every project you do, you have to know what the rock is underneath. There's all kinds of opportunities for test boring geologists. Anytime this is our drill rig over to the right, anytime it's running, there's a geotechnical inspector on site documenting the rock. A lot of contracts say, hey, you'll pay us for X amount of rock, anything more. So they kind of, sitting there identifying the rock, making sure nobody's getting ripped off. Environmental permitting specialists, hydrologists are involved, all kinds of geotechnical engineers, and work with geophysicists as well. When I was putting together this presentation, I was thinking about when I was sitting there getting ready to graduate, being nervous about entering the workforce. And I remember sitting there listening to the alumni speaker talk, probably in the back with my arms crossed with a crappy little frown on my face, going, well, that guy just got lucky. Well, this geotechnical services, Gregory Geotechnical Services is a startup company. When I started talking to them, they said they wanted someone with a geology background, somebody that had drilling experience, somebody that had estimating experience, and somebody that had project management experience. So I went, I guess I am pretty lucky. I put this little statement, luck equals preparation and willingness to accept opportunity when it presents itself, because every step of the way, whether I realized it or not, I was building the hard and soft primary and secondary skills to be ready for the opportunity. What you guys have spent the last 4 years doing is getting the foundation of that. No matter if you graduate and go right into it, geology field or not, you'll be acquiring skills for when opportunity does present itself, and you'll be just fine. Trust me, everyone is looking for young, smart geologists. There's a lot of opportunity out there. So I wanted to talk to you guys about some of the projects that we've currently got going on in Pittsburgh and the surrounding area. This is our drill rig. It's a CCM EK160. You look at the power pole in the back. That's basically what we're replacing these projects. This is one of 𝐤𝐴𝐚𝐿ight and Pittsburgh's main transmission lines that powers most of the city. All of these transmission poles sit on a deep foundation. So that right now we're piloting to drill this deep foundation. I'm talking maybe 10, 12 foot wide, 40 foot deep on average. Some seriously big holes. So you drill out a hole, you have to understand the geology underneath, drill out a hole, put some type of structural element in it, rebar, casing, what have you, and fill it with concrete so that these big zappy zaps don't fall over and Pittsburgh goes out of power. So That's our drill rig, that's our driller Jesse, that's my main man Bubba there in the green shirt. I included this, we got some drone footage. I chose this photo in particular because there's a lot going on here, that wouldn't, that doesn't make itself clear. Again, I said this all starts with an understanding of the underlying geology. So when we were bidding this project years ago, when they were bidding before I came along, they had to know, they would have got soil borings for the new hole. And they have to understand the risk associated with the underlying geology. So you can see a little creek there. And you can see the topography kind of goes up and it's kind of a cliff. Well, we're building in a brand new floodplain, or in a floodplain, new construction. So there's a lot of hazards associated with that. You got water, if you're gonna drill a big hole right next to a creek, there's gonna be a lot of aquifer forces underneath. So if we didn't take any measures, when we started drilling and that water pressure shoots up, everyone's gonna have a real bad day. Alternatively, if it did look good and we start pumping concrete, then it blows out on the side and screws up the screen. Nobody wants that either. So we had to do a lot of prep work in order to do this. We had to drive this casing, get this, my main man Bubba calls it a BFH. I call it a big freaking hammer. Drive 40 foot of casing in the ground. Just shoot a video of it running and it's not working. But anyways, it just drives it down. That's it. Imagine it driving 40 foot of casing. I don't remember what this was, 12 or 14 foot in diameter. That's a.
Does the video have sound?
No, I made sure it didn't have sounds just because I didn't, it's a construction site. But so anyways, we drive the casing, go in, drill it out. Because of the soil and water conditions here, you see those blue tanks up in the top left there, that's slurry. You gotta get a type of fluid, like thick drilling fluid to counteract the push of the water. So the consistency, the density of the slurry overrides the aquifer push pressure so that it keeps the hole open and everything like that. We have a big crane and we got to pump concrete. All of this, everything that you see in that picture is dictated by the local underlying geology and the understanding of it. When you're doing something like this, you have to consider all these things because all this stuff costs money. And if you're doing it in a business, you want to make sure your bases are covered and you really inspect the local geology. So that's one of the projects we got going on. This one was really interesting. This was for Norfolk Southern Railroad in Pittsburgh on, that's East Carson Street. I lied, it's West Carson Street. That picture on the far left is, you can see a railroad and we're building what they call a soldier pile wall. To my back, when I took that picture, the Duquesne Incline is like right behind me, if any of you are familiar with Pittsburgh. Acrisure Stadium, or I like to call it Heinz Field, is over to my right across the river. So what we had going on here, if you look at the picture on the right, they had this old crappy railroad tie wall that was probably like 100 years old and it was giving way, which was gonna undermine the stability of those railroad tracks. And nobody wants any train derailments. So we got contractors to come in and build what they call a soldier pile wall. Essentially, we're drilling down holes, placing beams and building a wall to stabilize that hillside so that the trains don't derail. Nobody wants that. But as we were drilling along here, you can see the orientation of my drill rig as we're kind of working our way out, building this wall. The drill rig weighs over 100,000 pounds. We're drilling along, and we keep noticing these cracks, these fissures, or as my main man Bob would say, the fissures. But how this works is you drill down so deep, you place your beam, fill it up so far with concrete, and you fill the rest with gravel. As we're going along, these beams are probably like on 8 foot centers, 8 foot away. As we're drilling along, you drill, and the gravel from the hole 8 foot away is now bleeding into our brand new hole. Oh no, this is bad. We're like, something's going on here, let's shut down for the weekend. We come back on Monday, half that wall's starting to give. Our 100,000 pound drill rig sitting up there and there's trains going by. There's a West Carson Street is down over that cliff. So we quickly identified that we're in a serious slide risk. This is a geotechnical hazard and a half. So we shut the job down, we get our engineers out there. And this is the picture on the far left is a sketch of kind of how we mitigated this. So we knew the fault lines were about 7 foot down. The railroad tracks to the left, cliff to the right. So we're only about a quarter of the way down with this wall. We're in a safety situation here. So we ended up designing this we call it the super highway, but essentially we built a bridge where we knew where the fissure was. So we would drill the beams down, pinning the slipping rock down into the good rock. So we basically built ourselves a pier on the way out so we could finish the installation of this wall. Here's a little picture of once we had all the vertical piles in, we'd go back and drill what they call tiebacks. Basically come in with a small rig, drill kind of at a 45, 30-degree angle, anchoring that whole entire wall back into the hillside. That was some pretty interesting stuff that we just did that last fall. Another thing we've been doing is these things called jacking bores. Essentially, this one was for Norfolk Southern Railroad 2, it was out near Johnstown. We had to high rail everything in. Essentially, on the left, the picture on the left, there's like a old culvert that's, I don't know, who knows, 100 years old that was clogged up and they want to put a new one in. So we bring our little jack and bore rig and actually push big pipe in through this, into the ground and drill everything out. Fortunately, sometimes you hit rock and you've got to play old school coal miner and go in and bust everything out by hand. Nobody likes that. We just did another one of these. They should be finishing up with it next week out near Harrisburg. Funny story about that one is we were going off the pre-bid. I was with my main man Bubba. He isn't a geologist, but he's been drilling for 40 years. He's old school, as he likes to say. And I wanted to impress Bubba. So with my geologic knowledge. So on these jack and bore jobs, they typically don't give you soil borings because they're typically in low fill zones. So doing a boring really wouldn't be ideal there. But anyways, I pulled up geologic maps and did my own research before we were heading to this meeting. And I was sitting there thinking, I was like, I think it's going to be a conglomerate limestone. I think we're going to hit it and we're going to have to bid for it and make sure we're covered from a cost perspective. We're driving out there. I'm like, hey, Bubba, what do you think? What do you think we're going to see out there? Gave him none of this information. He's like, it's going to be conglomerate limestone. I'm like, are you kidding me? And we ended up getting out there and, after the pre-bid meeting, once all of our competitors left, we're snooping around, looking around. I go down over the hillside, a big chunk of conglomerate limestone. So 2 different ways of looking at it, getting the same conclusion. But yeah, that's just 3 of the projects we've done in the last, 8 months. I find it interesting. That's my main man Bubba there again. A little old school. And then I didn't get a good picture on the tieback rig, but we were in St. Louis a couple of days, about a couple weeks ago looking at them, and that's kind of what a tieback rig would look like. So, does anyone have any questions?
So around Pittsburgh with there are lots and lots of subsurface mines.
Yeah.
And so some of the due diligence before you do big, huge holes like that is to make sure you're not gonna let the whole thing drop.
100% correct. So a part of this project, it's a 5-year project. One of the phases we did this past fall, there was a mine void and we bid accordingly for it. And once the contract, became an actuality, we received the contract, we went back to him and said, hey, given our means and methods, we might want to consider redesigning this. So we ended up widening it, shortening it, and so we were above the mine void. There was also an alternative option to extend it way down through the mine void.
Case it off or something like that.
Yeah, drive casing down, but I think there was associated rock with driving casing would be very difficult for us, or if not, nothing's impossible. Wouldn't be good from a cost perspective.
If you can get the movie to run, I'd love to watch it myself, but I'm the only one.
The link, is that your?
No, I should be able to play there.
Maybe.
So this is an AP 600. This thing really stressed me out because, you know, we had all these pieces.
Oh, so it's everything.
Yeah.
Yeah, sorry about that.
We had everything lined up to go to do this. This was like one of 24, 25 holes we would do last fall. And like 3 days before I rented the hammer from a company out of New Jersey, they called me and said, hey, your hammer's stuck on a barge in the Hudson. Like, dude, this cannot happen. Like so there's a bunch of hoops we had to jump through to make sure we get the hammer. We actually drone footage. I think that link is, yeah, so this is the site in McKees Rocks. We didn't get any photo or drone. The drone was not there the day we were drilling, but there's the slurry tanks, there's the brick. Again, all of this is driven from the underlying geology. Every piece of equipment we have there is calculated based on the understanding of the underlying geology.
And this is where you nonetheless ran into the big fracture. Things started to heal off. This is different.
This would be a couple,
That's the railroad.
Yeah.
Okay, yeah, my bad.
But all of these, I mean, there's 24 holes, some down kind of in the floodplain, some up on mountains. They all had their own challenges. Every hole you open up has its own challenges.
So here, it looks like you might have built that road in too for your equipment. I was gonna ask, what's the logistics for, I mean, these are big pieces of equipment that you're having to bring in.
Would you mind, going back to the presentation, the other link?
I will in a second, hold on. If I can.
Yeah.
I don't know how to do it. You might have to hit the escape button on the keyboard. Yeah, okay, that'll do it. Hold on, the back to it.
So,
This one here?
yes, no, it's the other one, but before you click that.
Yeah.
This project was phased over from 2022 to 2027. The reason being is, to get these outages during the spring and summer is like peak loading season from an electrical perspective. So we can only get the outages to take down the old towers, build these new ones in the fall and winter. Or else we kind of have some rolling blackouts and kind of be like our friends in California. But so all winter, spring and summer, we're building access roads and a lot of those, we actually have to drill walls because they're on the side of cliffs to get all of our equipment just to drill the holes. So that's what we've been doing these last, since this project wrapped up in January, this phase of the caisson work, we've been spending all the time and resources, building access roads. So when we have the next outage this fall, so if you click that other link,
Right here?
yep, that's kind of the main construction company, the Greater Construction, that does all of this. But here's one of our access roads. The left side of the canyon look exactly like the right. We built all this. Just you can see the work pads. A lot of resources, time and effort goes into these projects. There's construction pad. There's some soldier pile walls that we drilled, again, just holding up the hillside for this access road, just to get to where we can drill. It's pretty interesting, some pretty interesting stuff. And this is all temporary, so when this, once this new line is all in, we go back and pull all that, restore it, make the water run just how it used to. You can see all the E&S controls we have in. That's what I mean when I said there's a whole team of environmental people, there's electrical people, there's geologists, all working together to give Pittsburgh power.
And the compliance with the environmental regs, like sedimentation control and all that stuff, there's a whole, like you said, there's like whole other consulting firms that you might hire out to do some of that.
Exactly.
So there's a lot of jobs, I guess, is the bottom line.
And things in construction are constantly changing. This project's evolved 50 times, and there's constant RFIs. Hey, we think we can get in here. Let's talk to the environmental consultants. No, in accordance to your DEP permit, you can only affect this much. Okay, well, let's redesign a new plan. Yeah, there's a lot of careers in this field, in this geotechnical world, that I was excited to share with all you today.
Is this federal money or state money?
This is all power company money, which I do think some of it is subsidized for these like infrastructure improvement plans. There's things called LTIP, long-term infrastructure improvement plans, government funds to feed projects like this. Yes, sir.
Brock, for your position in this geotechnical company, do you need to be a licensed professional geologist or do you work with licensed PGs?
Nope.
No. Okay.
I am a geotechnical project manager, so
Yes.
at the core of what I do is the project management side, but I'm also involved in the estimating.
Mhm.
And the estimating is geotechnical heavy, you know, reading the borings to figure out, okay, how long is it, what materials, subcontractors and everything do we need to pull this off? And then when it's time to actually pull it off, managing the budgets, like on that drone footage, like I had to call all those people, organize them all for that day. When we get into the geotechnical situations, we'll, like, for example, if the plans change and we have to redesign something, I will subcontract out to a geotechnical firm, PGs, PEs, and they will re-engineer things per our conversations so that we can pull it off, which then also has to get approved by 10 other people with PEs. But I do work with several PEs, like that super highway I was telling you about. When that was a situation, I didn't have the power to draw that up, so we brought out our civil engineers. One of our president is a geotechnical engineer, so we had 3 or 4 different engineers look at it, communicate with the railroad our plan, and execute.
Follow up, how do you like the responsibility of your project management?
It can be stressful. Yeah,
I can imagine.
but it's exciting. It really is. When I was project managing the electrical field, I'm passionate about geology, geotechnical stuff. I wasn't passionate about electrical distribution and staring at 10,000 telephone poles a day, but being in the chaos of project management, I find very rewarding and fun. Seeing from an estimating perspective, putting numbers to it, seeing it come to life, calling all your subs, calling all your suppliers and pulling it off with my superintendent Bubba and our supporting staff is so heck of a feeling.
That's what Nick says about being checked.
Every day.
Another business where I've seen this dichotomy, the old way and the new way, like you mentioned, your way and Bubba's way, was 40 years ago when I was in my 20s working out in Nevada all the time, was the mining industry. Because a lot of people say, what are you doing? And I explain it. They thought this was very curious that you'd want to use structural geology or plate tectonics, figure out what you're looking at. They said, I just sit on the rock and it tells me if there's gold in there. And back then that still kind of worked, but then we got into these new frontiers where you really did have to do methodical. And it's changed a lot, but I was considered full slav of those early days, trying to be methodical. But
anytime we're looking at how we're gonna pull anything off, you know, we pull in the PEs, myself in the conversation, we pull off Bob with the superintendent, you know, so you got a different perspective of old school fella, with 40 years of drilling experience. You got a geotechnical engineer and somebody that's kind of looking at the cost side too, when we all put our heads together.
Does Bubba have his own like stamp? Like
He likes to say it. He does. He calls it an OE stamp, an operating engineer stamp. And he tried to stamp that little sketch I had because he was the one that drew it up, and we said, no, we gotta get a PE.
So the one you showed us was yours on the field book.
That was Bubba's.
That
He
was
drew that
Bubba's, okay.
up. And once we kind of took some measurements and got an idea of what was going on, that was an OE stamp. There was other drawings.
Yeah. The final,
Yes.
the final one, I could, yeah.
So Brock, it's really good to see you again, first of all, but also how far you've come since you were here. You certainly learned a lot on the job. I think you got some of the foundations that you mentioned while you were here. I'm just wondering if there's something that, from your perspective now, that you wish you had gotten back in the undergraduate training you had that you didn't get that was been really helpful for you.
Yeah, stuff like this is so specialized that I don't think that this is kind of an academic setting, you know, tailored for going on to grad school and things of that nature. I don't know if you can really lecture that without really getting to the nitty gritty. Self-admittedly, I do kick myself in the butt a lot because I wasn't the best student. I wasn't as involved, and I really wish I was. I think there was a lot of opportunities that you guys provided that I was too busy hanging out at the frat house to, be a part of. But some of the things that have helped me out the most is those rough and dirty maps, the spatial drawing things out in a quick way. More labs that kind of require those skills would be beneficial, I think. I mean, once I map all these projects out on Google Earth when I'm bidding them, just so I understand it. But once I show these old timers that I can send them a Google Earth file and they can pull it up on their phone and drive around and see the project around them, it absolutely blew their mind, and that got me a long way.
I'm really glad you found something more durable than the glassware in my lab.
It's pretty tough to break these beams, but we find ways sometimes. And similar, I forgot to mention this, similar to all those other tools in the oil field that I was talking about, there's tons of specialty instrumentation that pertains to everything in this geotechnical realm, and tons of opportunities out there. In this construction field especially, we're looking for more women, we're looking for more minorities, we're looking for young people in general. Like, it's literally, in our office, it's me, a 30-year-old PE, which I have an immense amount of respect for, and everyone else is in their 50s. I don't know where all the 40-year-olds are, but I haven't seen them.
So Bubba's not 40.
No, he's 62. And he's a pain in my butt, so I love it.
Do the students have any questions, Brock? All right, well, let's thank them again. All right, that officially ends our Geoscience Day presentations. Thank you, really appreciate that. I believe one or two of the students are gonna take Brock out to lunch. Josh, are you involved in that? Is that what Katie said?
I actually forgot to ask Brock if he has time to stay.
Oh, Brock, do you have time?
I think I can pencil it in.
Okay.
If anybody else would like to go along, please, meet up with Josh, and I don't know what the plan is, but maybe Katie has a plan as to where they're going. I don't know any of the details, but if you're interested, if you'd like to talk to Brock a little bit more, get some, pick his brain about some things not in front of us, by all means, join him for lunch. And just thank you all once again for coming today. We really appreciate it, and congratulations, students. You all did a really just phenomenal job. Well done.